Hi, are you considering changing career paths and need to decide what to focus on? Or are you thinking about studying to become a computer networks administrator or engineer? Look no further. This is a course for complete beginners where the most crucial terminology, concepts, and current technologies are explained in the simplest way possible, focusing on helping you truly understand the topics. Here's what we will talk about. First, there's an introductory section where the basic of the basic terminology is introduced, which we will be using throughout the course later on. Then we go through the layers of the OSI model, which is also explained in the introductory section, so no worries there. In the application layer section, we'll discuss some of the most important protocols that pretty much make the internet of today. And also, they are the protocols you already use. I tried to give you some examples to help you easily get a grasp of what those protocols actually do, why they're there, and we even discuss security issues related to some of those protocols. Next up is the transport layer, where we have the two stars, TCP and UDP. Do pay extra attention to those lessons, as TCP and UDP are quite important. Anyway, next section focuses on the network layer, where we talk about the IP address, again, protocols such as DHCP, ICMP, NAT. We also talk about routing and routing protocols, just enough for you to be informed and know the gist around it. The final OSI model layers for us are link and physical, where we discuss switching, the MAC address, virtual LANs, ARP, and its security flaws, with some examples too. We touch upon mobile and wireless networks briefly, as it is not the main focus of this course. However, I believe that you will find points covered in that section rather useful and hopefully interesting too. And finally, our last section is on computer networks security, where today's top malicious attacks are highlighted, as well as two most important network security devices, or call them concepts, firewalls, and intrusion detection / prevention systems. One thing to keep in mind, although I do mention this in the lessons too, there will be simulation files available with the lessons that do have a simulation included, and you can find those under the lesson itself in the resources part. The simulations are made in Cisco Packet Tracer, which is free, and I actually have a free course on how and where to find it, download it, install it, and even some basics on using the software. However, you don't have to even download the files. It's enough to just watch the lessons. I do everything for you in the videos. Wow, now that I've listed all of that, it does sound like a lot, but again, those are just the fundamentals. All right, let's get into learning. Good luck, and let me know what you thought of the course. Hi, welcome to the course. Before we get into the fun part, let me introduce myself. I'm Dunja, I'm a cybersecurity expert, and before that, I held a job as a teaching assistant at a faculty of computer sciences, teaching exactly the topic of this course, computer networks. The reasoning behind this course is very simple. It was you, my Udemy students, who requested it. So one day I said to myself, why not? I'll try to explain the foundations of computer networks in the simplest way possible. Exactly how I did it when teaching at the university, which gave fantastic results. Therefore, I'm hoping it will work for you too, and that you'll find it useful for your academic needs or your professional career. Either way, I'm eagerly waiting for your feedback. Enjoy. Welcome. Today we'll learn the following. What is a computer network? And also, what are some other types of networks? Let's go. So, according to Amazon Web Services, the term computer network refers to interconnected computing devices that can exchange data and share resources with each other. Let's dive into that a little bit. We're talking here about computing devices that are interconnected and can exchange data and resources with each other. And that would be the simplest definition of a computer network. However, there are other categories of networks. Some of those are Internet of Things, are basically groups of physical devices or objects with sensors, processing ability, software, and other technologies that connect and exchange data with other devices and systems over the internet or other communications networks. There are wireless networks, same as any other network really, only without cables. This technology uses a variety of radio communications. Mobile or cellular networks are what your smartphone uses to communicate to your mobile operator's base stations or telco towers. As for SDNs, short for software-defined networking, that is an approach that uses software-based controllers or APIs to communicate with underlying hardware infrastructure and basically direct traffic on a network. This technology is used quite a lot nowadays, especially in the cloud, which we will talk about later in this course. And finally, we come to this term air-gapped network. And in essence, that is a cybersecurity term and concept in general. It describes a network that is not connected to the public internet. Furthermore, it's not only not connected, but is also physically segregated from other networks as well as the internet. We'll discuss the internet in our next lesson, so stay tuned. We will mention the term internet a lot in this course. So let's clarify exactly what internet is. Per Technopedia definition, the internet is a globally connected network system facilitating worldwide communication and access to data resources through a vast collection of private, public, business, academic, and government networks. Now, the terms internet and World Wide Web are often used interchangeably, but they are not exactly the same thing. The internet refers to the global communication system, including hardware and infrastructure, while the web is only one of the services communicated over the internet. Are there other services, you might wonder? Of course there are. Internet can be entirely described as an infrastructure that provides services to applications. These applications include electronic email or electronic mail, which email is short for, web surfing, social networks, instant messaging, voice over IP, which is VoIP. VoIP is short for voice over IP, video streaming, distributed games, peer-to-peer, or P2P is short for that. Peer-to-peer is mostly used for file sharing, television over the internet, remote login, and much, much more. The applications are said to be distributed applications since they involve multiple end systems that exchange data with each other. Importantly, internet applications are run on end systems. They do not run in the packet switches in the network core. That's the basics of the internet. We'll explore more in the rest of our course, so let's get going. Another important term for us to learn and definitely remember is a network protocol. The textbook definition of a network protocol is a network protocol is an established set of rules that determine how data is transmitted between different devices in a network. Now, the mentioned network can be a local network and the devices might be directly connected, or it could be a public internet network, such as the World Wide Web, where the devices are in different parts of the world, but they're communicating directly as if they were directly connected. That is the beauty of computer networks, my friends. Now we're going to use a human analogy as an example. If you haven't heard of them already, Alice and Bob are actually quite famous in the world of computer networking. They are fictional characters, commonly used as placeholders in discussions about network protocols, as well as cryptographic systems and other situations too. Basically, what happens in this example is the following. Alice on the left says hi to Bob, the person on the right. He responds hi. She then asks for the time and he tells her that it's 2 o'clock. On the right-hand side, we have a computer, a client, establishing a TCP connection to a Udemy server. By the way, don't worry about TCP for now. We'll discuss it later on more thoroughly. Anyways, the PC sends a connection request, server accepts it. The computer then sends a HTTP request, to which the server also replies with a requested file. One important thing to understand here is that, let's look at the example on the left. If this is all of this protocol, meaning there are no other specifications, then this communication between Alice and Bob can only go one way. First, she must say exactly hi to him first. If she says something else, or he's the first one to communicate, it's not going to work. Also, she can only ask about the time, and he can only tell her time in the format specified in the protocol. Her application side will be programmed to only understand what is defined in the protocol. Of course, this is only one example, and during this course, we will go through many more. Some of the most popular protocols that we can quickly cover right now are the ones displayed here. Let's go through each one. TCP is a popular communication protocol which is used for communicating over a network. It divides any message into series of packets that are sent from source to destination, and there it gets reassembled at the destination. HTTP basically is what you use to browse the web, or more specifically to see websites. It's short for Hypertext Transfer Protocol, and its updated version, which includes security, is HTTPS, which is short for Hypertext Transfer Protocol Secure. SMTP, on the other hand, is short for Simple Mail Transport Protocol, and it's designed to send and distribute outgoing emails. Now, you might ask, well, if SMTP is only used for sending the emails, then how do I receive them? Well, you would use another protocol for that. That one is called POP. It's short for Post Office Protocol. Then FTP is what you will use for transferring files, and similarly to HTTP, FTP also has a secure version. It's called SFTP for Secure File Transfer Protocol. Telnet is a protocol specifically designed to enable remote login, but it is highly insecure because it transfers everything in clear text. Its secure alternative would be the protocol called SSH, but we will talk about that later on. And that would be it for this very short lesson on network protocols. As you already might guess, we will discuss these in much more detail in the upcoming lessons. Now that we have learned what is a protocol, it's time to figure out how to categorize network protocols. The OSI model, short for Open Systems Interconnection, describes 7 layers that computer systems use to communicate over a network. Those 7 layers are application layer, which holds some of the protocols we already mentioned, such as HTTP, FTP, and SMTP. Presentation layer, whose role is to provide services that allow communicating applications to interpret the meaning of data being exchanged. These could be data encryption and then decryption on the receiving end, or, for example, data compression. Session layer provides for delimiting and synchronization of data exchange, including the means to build a checkpointing and recovery scheme. If this sounds a bit too abstract for the moment, don't worry, we'll talk about these things more as we move forward. Next, we have the transport layer, and we will certainly talk more about the 2 protocols most important here, and those are TCP and UDP. In essence, transport layer transports application layer messages between application endpoints. Next, the network layer, also an important one. This layer is responsible for moving network layer packets, known as datagrams, from one host to another, and it consists of perhaps the most important network protocol of them all, the Internet Protocol, or IP. Data link layer consists of protocols specific to the type of connection being used in the network. We'll discuss it later in more detail, but for now, know that examples of data link layer protocols are Ethernet, PPP, which is short for point-to-point protocol, HDLC, which is actually a group of data link protocols, etc. And finally, there's the physical layer, which literally looks at individual bits and moves those around the network. Again, we'll get into more details about it later on. Now, let me give you a few more details while we're here. First off, the OC layers are numbered from bottom up, meaning physical layer is called layer 1. And then we move upwards. Therefore, network layer is layer 3, transport is L4, and application layer is L7. And the first 3 layers we can call software-based, meaning you don't need any special hardware devices to perform the functions of the protocols belonging to these first 3 layers. And the last 3 layers are hardware-based, meaning you need a link, an interface, and then on the network layer, a switching or a routing device. And then in the end, the transport layer is left without a label here, but it is more software-based than hardware. However, we call it the heart of the OSI model, and you'll see later why. And now one last thing, I promise. For each layer, there is a name for the piece of information we are transferring over a network. We tend to call these pieces of information packets, but as you can see here, it's technically only called a packet while on the network layer. On the application, presentation, and session layers, that piece of information is called a message. On transport layer, it's a segment. On network layer, I want to point out that there are two names in the literature, packets and datagrams. And on layer 3, it's a frame. And then finally, on the physical layer, on layer 1, it's a bit. All right, in our next lesson, we'll look at a practical example, so see you there. All right. Now that we've established the OSI layers, let's go through a practical example, just to make sure you remember what it's all about. In the little network we have up here, we're going to imagine that computer X sends a message to computer Y. What happens in the background is displayed here. Let's say that X sends Y a photo. That's the original message, which is then compressed on the presentation layer. After that, a session is established. And then on the transport layer, we must choose basically between speed and reliability. We'll talk about this more. Don't worry about that. But if we need quick delivery and we don't care if all of the bits, in this case, all of the pixels of our picture are delivered, then we'll choose the less reliable UDP protocol. Otherwise, we'll go with TCP. Next, we add our and the receiver's IP address on the network layer. The data link layer will add the MAC address. And then finally, on the physical layer, all of that is sent bit by bit over the network. Now comes the important part. Once the packet or user X's photo reaches a network device, in this case router A, the router doesn't support all 7 OSI layers, but only 3, as it's a network device. It goes only up to layer 3, so it actually doesn't even look at the data, but only those parameters we mentioned were added on the first 3 layers. First, on the physical layer, there are bits, obviously. Then on the data link layer, there's the MAC address. And then on the network layer, there's the IP address. Then once router A reaches the 3rd layer, it packages the packet again with the data needed for the first 3 layers. And yeah, this process repeats for each device until the packet reaches its intended destination, which in our case is computer Y. Only then the packet is opened all the way to the application layer, where we will find our photo. And now a bonus, we'll use a simulator to look at this example. I'm using Cisco Packet Tracer program. It's free. And I have a course about it. It's also free, so check it out on Udemy. Let's get into it. All right, what we will do here is we will simulate this computer sending something to this computer. It's a bit more complicated to send something on the application layer, so we'll start with a simple ping. In order to be able to do that, I need the IP address of this computer, and the IP address is 10.2.0.10. So 10.2.0.10, I'm going to say ping 10.2.0.10, and let's see if it succeeds.
So the first one timed out because I just switched on this entire network. So once you run the simulator, it will kind of simulate everything starting from the beginning, meaning booting up the switches and the routers. So by the time the routing tables exchange all the routes and all the MAC addresses become known in the network, which we will talk about later on in our course, the first ping is therefore going to fail, but the second one and the third one and the fourth one were successful. Now, there is a way to do this in the Cisco Packet Tracer that is more graphical, and we will use that so that we can better understand what happens in the network. Let me zoom out a bit. All right, what I'm going to do is I'm going to send this. This is also a ping. So I'm going to click here. This is the sender of the ping, and then this is the pinged device or the receiver of the ping. So when I first initiate the ping, I'm now in the simulation mode. So I'm looking exactly what happens in real time. So this packet doesn't really travel down the link until I click on the next step, basically. But I'm interested to see what happens in the first step. So basically, we are looking at all the OSI layers on this computer. And basically, you can see that there are in layers and that there are out layers. So basically, in layers means that this is what I see when I receive the packet, when it's on the receiving side of my interface. But in this case, I'm sending out a packet, so I can only see the out layers. And then you can read the whole process. You can read exactly what happens step by step. So the ping process starts the next ping request, and then basically we fill all the needed parameters, such as the IP address, the port, etc. On the OSI layer 2, which is the data link layer, we talk about ARP and we talk about the MAC address. Again, this is something we will discuss later on in the course. And then on layer 1, we are interested on which interface we are going to send out the frame. If I move through this network, I'm going to speed this up a little bit. My packet reaches the switch. Now, a switch is a layer 2 device, so it cannot look at any layer above layer 2. So it doesn't have the networking function. So it doesn't have the network layer either because it doesn't need it. And you will see that the switch receives the packet on the incoming side, on the incoming interface, and then it sends it out again on the outgoing side. And as you can see here, we receive the frame on Fast Ethernet 0/1 interface, and then we look at the MAC address because that's all a switch can do. And then when we are sending out this frame at this point, remember that here it's called the frame. We are sending it out again through an Ethernet port, and the port this time is Gigabit Ethernet 0/1 because that's this interface used here to connect to router A. Once the packet reaches router A, now again we have the 3 layers. And the difference here is that now we need to look at routing because there are several hops between computer X and computer Y. So we need to figure out what is the best route and if there is a route at all to reach the other computer. So we're looking at the routing table. The routing table finds a routing entry. This was of course pre-configured by me. We will talk about what exactly happens in here, what exactly we need to do to be able to correctly fill the routing table. But then again, the router also has layers 2 and 1. And the packet is sent out through router 1 and then to router C and then to switch 2. Again, on the switch, we only have 2 layers. If we go to the computer receives the ICMP. Now, the ICMP is an echo packet. That means that once the receiving computer receives it, it is expected to return the packet as a response, just to let the sending computer know that it received the packet. Over here, you can also look at the frames themselves and at all the parameters that are in there, but we will discuss those in more detail later on. If we go all the way until the end of the simulation, our packet will reach the initial sender, and we will see this check mark here, which means that the ping was successful. All right, that would be it for this lesson. See you in the next one. So far, we've discussed only the OSSI model. However, there's several more you'll find in literature or we'll hear about from other network administrators. Let's get right into it. In the middle, we have OSSI, just so that we can compare it easily to the other two. The model on the left, DoD, is short for Department of Defense, and we're talking here about United States of America Department of Defense. That model consists of 4 layers instead of the 7 layers OSSI has, and actually that is the main difference. First 3 layers, application, presentation, and session, are merged together in a process application layer. The 2 middle layers are simply called differently than the OSSI one, and then the bottom 2 layers are again merged together. And actually, the similar is the case for the TCP/IP model, or as some call it, the Internet Protocol Stack. You will find this phrase in some literature instead of the TCP/IP model. Here, the first 3 layers are again merged. There's transport and network layers, and then finally, physical and data link are merged again, and they are called network interface in this model. Anyway, this course will follow the TCP/IP stack, meaning we will have 4 main sections to describe the Internet's protocols. That's all you need to know about the different network models. It will become more and more clear how these things work as we move through the course. So, see you in the next lesson. Now that we've gone through the basics, let's review the history of computer networks, shall we? The history of modern computer networking technology goes back to 1969, when ARPANET, short for Advanced Research Projects Agency Network, became the first connected computer network. It implemented the TCP/IP protocol suite, which later became the Internet. ARPANET was developed by the Advanced Research Projects Agency, which is what ARPA stands for, and it is a subset of the US Department of Defense. Why did they need to develop networked computers? Well, because of the Cold War, of course. The first 4 nodes, however, of the ARPANET were connected using 50 kilobit per second circuits between the University of California at Los Angeles, the Stanford Research Institute, the University of California at Santa Barbara, and the University of Utah. Now let's see what the development of networks looked like in Europe. CICLED Computer Network was a French research network created in the early 1970s. It was one of the pioneering networks experimenting with the concept of packet switching, And unlike the ARPANET, it was explicitly designed to facilitate internetworking. For those of you who might not know, internetworking is the practice of interconnecting multiple computer networks, which is what the internet looks like today. Let's finally talk now about the modern internet as we know it today. Well, the main event of the 1990s was the emergence of the World Wide Web application, which brought the internet into the homes and businesses of millions of people worldwide. The web served as a platform for enabling and deploying hundreds of new applications that we take for granted today, including search, such as Google and Bing search engines, internet commerce, for example, Amazon and eBay, and social networks such as Facebook, Instagram, TikTok, etc. The second half of the 1990s was a period of tremendous growth and innovation for the internet, with major corporations and thousands of startups creating internet products and services. By the end of the millennium, the internet was supporting hundreds of popular applications, including 4 killer applications: email, including attachments and web accessible email, the web, including web browsing and internet commerce, as already mentioned, instant messaging with contacts lists. This was novelty back then. And then peer-to-peer file sharing. Initially, we shared MP3s, for example, and this was pioneered by Napster. And as the saying goes, the rest is history. See you in the next lesson. In this lesson, we'll once again revisit the definition of the application layer, talk about its place in the OSI model, discuss some of its functions, and list some of the most used protocols that reside on this layer. So what is the application layer? The application layer sits at layer 7, the top of the Open Systems Interconnection, OSI, communications model. It ensures an application can effectively communicate with other applications on different computer systems and networks. It's important that you understand that the application layer is not an application. Instead, it is a component within an application that controls the communication method to other devices. It is an abstraction layer service that masks the rest of the application from the transmission process. The application layer relies on all the layers below it to complete its process. At this stage, the data or the application is presented in a visual form that the user can understand. Let's see what are the functions application layer is responsible for, and all of this will become way more clear. First, application layer ensures that the receiving application is identified, reachable, and ready to accept data. When appropriate, application layer enables authentication between devices for an extra layer of network security. Application layer protocols define the types of messages exchanged, for example, request messages and response messages, and also when those are sent and how. It ensures agreement at both ends on error recovery procedures, data integrity, and privacy, determines protocol and data syntax rules at the application level, and finally, application layer is responsible for presenting the data on the receiving end to the user application. Finally, let's see the most popular protocols that reside on this layer. First, and we can freely say the most popular one is HTTP. We've already mentioned it. It supports the web application. It uses port 80 and the underlying transport protocol is TCP. We'll discuss TCP versus UDP in more details later on, but for now know that TCP is more reliable and UDP is faster. Next, we got file transfer, which is supported by the FTP protocol. FTP uses two ports, 20 and 21, and we'll get into more details later on. Of course, when you transfer files, you want the file to arrive to the receiver in its entirety, so naturally it uses TCP as its transport protocol. Next, there's email. Email as an application is supported by several different protocols, including SMTP, POP3, IMAP, but it can also use HTTP. We'll discuss this further in a lesson dedicated to email. Next, there's remote access, and here the example for that is Telnet. However, there are more secure alternatives available nowadays. Telnet uses port 23 and the transport layer protocol is TCP. Last but not least, an example of an app residing on the 7th OSI layer is internet telephony. There's several protocols supporting it, SIP and RTP, short for Session Initiation Protocol, and Real-Time Transport Protocol are kind of industry standards, but there are other proprietary protocols such as Skype. However, Skype belongs to this category of application layer internet tools. And finally, internet telephony is one of the few services that uses UDP. Why? Well, if you miss out on 1/10 of a second during a phone conversation, it's barely noticeable. It is way more important that the voice is transferred in real time than to be complete. As promised, we'll discuss TCP and UDP in the transport layer section of this course, but now let's continue learning about the application layer. See you in the next lesson. There's only one more thing to cover before we jump into the protocols themselves. Network applications architecture, designed by the application developer, will likely be one of the two predominant architectural paradigms used in modern network applications. Those are the client-server architecture or the peer-to-peer architecture. Peer-to-peer is also known as P2P, where 2 is the number 2. Let's see what each of those looks like. In a client-server architecture, there is an always-on host called the server, that's this blue device on the top of our picture here, which services requests from many other hosts called clients. A classic example is the web application, for which an always-on web server services requests from browsers running on client hosts. When a web server receives a request for an object from a client host, it responds by sending the requested object to the client host. Note that with the client-server architecture, clients do not directly communicate with each other. For example, in the web application, two browsers never directly communicate. Rather, each host talks to the server. Another characteristic of the client-server architecture is that the server has a fixed, well-known address called an IP address, which we will discuss soon. Because the server has a fixed, well-known address, and because the server is always on, a client can always contact the server by sending a packet to the server's IP address. Some of the better known applications with a client-server architecture include the web, FTP, and email, for example. In a P2P or peer-to-peer architecture, there is minimal or no reliance on dedicated servers in data centers. Instead, the application exploits direct communication between pairs of intermittently connected hosts called peers. The peers are not owned by the service provider, but are instead desktops and laptops controlled by users, with most of the peers residing in homes, universities, and offices. Because the peers communicate without passing through a dedicated server, the architecture is called peer-to-peer. Many of today's most popular and also traffic-intensive applications are based on P2P architectures. These applications include file sharing such as BitTorrent or internet telephony such as Skype, and also IPTV in some instances. One of the most compelling features of P2P architectures is their self-scalability. For example, in a P2P file sharing application, although each peer generates workload by requesting files, each peer also adds service capacity to the system by distributing files to other peers. P2P architectures are also cost-effective since they normally don't require significant server infrastructure and server bandwidth, in contrast with client-server designs with data centers. That's that on the two main application architectures, peer-to-peer and client-to-server. Let's now go ahead and learn about how those are used in some of the most popular application layer protocols. Finally, let's talk about HTTP. The Hypertext Transfer Protocol, HTTP, the web's application layer protocol, is at the heart of the web. It is defined in RFC 1945 and RFC 2616. RFC is requests for comments. These are online, freely available documents that basically define network protocols. HTTP is implemented in two programs, a client program and a server program. The client program and server program, executing on different end systems, talk to each other by exchanging HTTP messages. HTTP protocol defines the structure of these messages and how the client and server exchange them. Now, before explaining HTTP in more detail, we should review some web terminology. A web page, also called a document, consists of objects. An object is simply a file, such as an HTML file, a JPEG file, a Java applet, or a video clip, for example, that's addressable by a single URL. And then most web pages consist of a base HTML file and several referenced objects. For example, if a web page contains HTML text and 5 JPEG images, then the web page has 6 objects, the base HTML file plus the 5 images. And finally, a URL, short for Uniform Resource Locator, is basically an address given to any unique resource on the web. And yes, you guessed it, in this scenario, resource is a synonym for object. Let's talk a bit more about URLs. The base HTML file references the other objects in the page within the object's URLs. Each URL has two components: the host name of the server that houses the object, and the object's path name. So in our example here, www.udemy.com is a host name, and coursex/text.docx is the path for object text, or excuse me, not text, but test, test.docx. The HTTP protocol is actually all about defining how web clients request web objects from web servers, and then how those requested objects are transferred back to the client. Let's look into that a bit more closely. Similarly to the scenario from our previous lesson, we have a server and a few clients. First of all, a web client is nothing more than a web browser, so technically one physical computer could represent several web clients, as one user logged in on one computer could run several web browsers at the same time. But for the sake of simplicity, we'll assume that each of those physical computers is one web client. In a nutshell, HTTP protocol describes how web clients request web objects, and then how the server sends those objects to clients. And now let's see what the protocol actually defines. First, the HTTP client needs to initiate a TCP connection to the server. In our example, that's www.udemy.com on port 80. Next, the HTTP client sends an HTTP request message to the server. The request message includes the path name /coursex/test.docx. Then the HTTP server process receives the request message, finds the requested object, in this case that's test.docx in its file system. Then it encapsulates the object in a HTTP response message and sends the response message back to the client. And finally, the HTTP client receives the response message. The TCP connection then can be terminated. Here's an example of a typical HTTP request. Get is the command for retrieving an object from the website. Then behind get, we have the object path. After that, the HTTP version is specified. In this case, version 1.1 is used. Then we have the host, udemy.com. Next is something interesting, and that is type of connection. Closed means that the client prefers to open a new connection each time it requests something from the server. An alternative to that would be a so-called persistent connection, which would mean that the client would open a TCP connection and then keep it open for a certain amount of time until it's done with requesting and receiving objects from the server. Next, we have user agent and language. Those are pretty self-explanatory. We're telling the server what browser we're using and what language we prefer to receive the object in, if possible. For some reason, this person wants to receive the web page in French. After request comes response. Here the protocol version is repeated, and then we have the code. This time it's 200, and in the next slide we'll go through what that means and some other codes as well. But for now, this means that everything is okay. The server has the object we're looking for, so it confirms the type of connection. Next, date is current date and time. Then a server version is listed. Apache is one of the most popular web servers you'll see, and you will see that in a lot of these messages. And then there's the last modified timestamp. Unlike the current date and time, this one tells us when the object we've requested was either created or last modified. It's actually more important than it might seem at first, because this is heavily used for caching. In short, your computer will cache this document, and then if you try to download it again, instead of downloading the file again from the server, it might just check the last modified field. And if there were no modifications to the file since you've downloaded it previously, then it will simply display the cached version to you. That way, time and bandwidth are saved, and you still get the latest version of the file anyway. So it's a win-win situation. Next, there's content length. It simply tells us the number of bytes in the object we have requested. And finally, there's a content type field. Obviously, that tells us what kind of content we're dealing with. And as promised, we'll go through some of the HTTP codes you should be familiar with. First, 200 OK means that the request was successful and the requested object is returned in the response. 301 moved permanently means that the requested object has been permanently moved within the server's file system. The new URL is specified in a field called location. The client software, as we already established, the web browser, will automatically retrieve the new URL. Next, 400 bad request. This is a generic error code indicating that the request could not be understood by the server. So the client made a mistake in forming the request somewhere. This usually means that the web browser or the HTTP client, whatever that is on client side, has not implemented correctly the HTTP protocol. Then 404 not found. It means that the requested object does not exist on this server. And finally, 505 HTTP version not supported. The requested HTTP protocol version is not supported by the server. You saw that little field HTTP version in request and response. In our case, both the client and the server used 1.1. So it all worked out. And that's it for HTTP protocol. This was a bit longer, but we've covered in this lesson some important concepts that will help us understand other protocols more easily. See you in the next lesson.
Let's mention HTTPS real quick. What is HTTPS? Hypertext Transfer Protocol Secure is an extension of the Hypertext Transfer Protocol, which we just covered in our previous lesson. More precisely, it's a combination of HTTP and SSL, short for Secure Socket Layer Protocol. It was created as a secure alternative to HTTP, but nowadays it's widely used on the internet. In our previous lecture, we used this URL as an example. That was the plain HTTP URL, and this is what HTTPS one looks like. In case you don't see the difference, there is an S added right after HTTP and before the colon. Now, a simple letter in the URL, of course, can't be the entire difference, and it's not. The main differentiator between these two protocols is encryption. Let's revisit our HTTP example of communication between a web client and a web server. In HTTP, the client requests something, usually a web page, and the server sends it back. And now here's the twist. In clear text, if you were to use HTTPS, that communication would be encrypted. In most literature, you will see that SSL is referenced as the encryption protocol used by HTTPS. However, SSL was mostly replaced by TLS and is now used by HTTPS. But what are these protocols? Per definition, SSL and TLS are cryptographic protocols that encrypt and authenticate data transfer between servers, systems, applications, and users. Now, TLS has already replaced SSL, and you should definitely be using TLS, and you likely already are. However, you might still see something like an SSL certificate, but don't worry, that's mostly due to branding issues. Most major certificate providers still refer to certificates as SSL certificates, which is why the naming convention persists. And since we just now mentioned certificates, and also one of the uses mentioned for TLS was authentication, let's see how does that actually work. When you go to a website, let's say udemy.com, what happens in the background is that your web browser will ask the web server to identify itself. The browser, or excuse me, the server will then send a copy of its SSL certificate, which is then checked by the browser by contacting the certificate authority. And what is a certificate authority, or for short, CA? CAs are trusted bodies that issue, sign, and store digital certificates, but this is all done by your browser automatically, so you don't need to worry about these. And that's it for this very short lesson. In essence, HTTPS compared to HTTP adds two very important functions, which is encryption of the traffic exchanged between web client and web server, and also authentication. All right, see you in the next lesson.
HTTP and FTP are both actually file transfer protocols and have many common characteristics. For example, they both run on top of TCP. However, the two application layer protocols have some important differences. The most striking difference is that FTP uses two parallel TCP channels or connections to transfer a file: a control connection and a data connection. The command, or otherwise called the control connection, is used for sending control information between the two hosts, information such as user identification, password, commands to change remote directory, and commands to download or upload files. And then, as the name suggests, the data channel is used for actual transfer of files from one side to another and vice versa. Another information you should know is that since FTP uses two connections, it also needs two port numbers. 20 is used for the transferring of files, and 21 is used to send the commands. Which commands are we sending though? First, there's the user command to send the user identification to the server. Then there's the command to send over the password. Then once you're logged in and you need to see the contents of a folder, you use the command list. The list of files is sent over a data connection, by the way, not the command one. The command itself is sent over the command channel, but the data itself, the response, goes through the data channel. Then there's the command retr and then the file name. It's used to retrieve, that is, to get a file from the current directory of the remote host. This command causes the remote host to initiate a data connection and to send the requested file over a data connection again. And finally, store file name. It's used to store, that is, put a file into the current directory of the remote host. Now, similarly as with HTTP, FTP protocol also defines the replies FTP servers can create. Here we'll look at some of the most common ones, and you can always find the complete list in the RFC document. FTP is defined in RFC 959, by the way. All right, so we have 4 responses here, and they're all pretty self-explanatory. Code 331 basically asks you for the password. 125 tells you that the data connection is already open and that the transfer is about to begin. 425 tells you that there's a problem and the data connection can't be opened. And finally, 452 tells you that the file you wanted to upload has not uploaded correctly. Usually you'll just need to try again in that case. In the end, I wanted to note that there's a simplified version of FTP. It's called TFTP, short for Trivial Transfer Protocol, Trivial File Transfer Protocol, excuse me. The main differences are that unlike the FTP, TFTP uses UDP. Port number is 69. There is no need for authentication. And if by any chance you need to know more, as always with these standard protocols, all the information is freely available in the request for comments document. And for TFTP, that's 1350. And in the end, where would we use TFTP? Well, it's used, for example, in VoIP devices inside an intranet. So, for example, in networks that are not exposed to the public internet, and so there's no fear of it being exploited. Or you might use it for simple devices that do not support some of the options FTP has, like authentication, for example. Okay, that's it for FTP and TFTP. See you in the next lesson. As you're probably all familiar with email, this should be an easy lecture. We'll talk about 3 protocols in particular: SMTP, POP3, IMAP, and then we'll mention webmail as well. Let's go. Let's start with SMTP. SMTP, short for Simple Mail Transfer Protocol, is defined in RFC 5321. SMTP transfers messages from senders' mail servers to the recipient's mail servers. Additionally, SMTP uses TCP and it has the client-server architecture. Let's explain it with an example. We'll use our Computer Networks World celebrities, Alice and Bob. First, let's say that Alice invokes her user agent for email, provides Bob's email address, for example, bob@udemy.com. She composes a message and instructs the user agent to send the message. Next, Alice's user agent sends her message to her mail server, where it is placed in a message queue. The client side of SMTP, running on Alice's mail server, sees the message in the message queue. It opens a TCP connection to an SMTP server running on Bob's mail server. So Alice's mail server connects to Bob's mail server via a TCP connection. After some initial SMTP handshaking, the SMTP client sends Alice's message into the TCP connection. At Bob's mail server, the server side of SMTP receives the message. Bob's mail server then places the message in Bob's mailbox. Finally, when he is ready, Bob invokes his user agent to read the message. Okay, Bob got his message, but Bob did not use SMTP to get his message from his mail server. For that part, Bob has to use another protocol, this time a protocol for mail access. And currently, there's a few popular protocols out there, including POP3, IMAP, and HTTP. Let's review each one. POP3, short for Post Office Protocol, is an extremely simple mail access protocol. It is defined in RFC 1939. And because the protocol is so simple, its functionality is rather limited. POP3 begins with the user agent or the client opening a TCP connection to the mail server on port 110. With the TCP connection established, POP3 progresses through three phases: authorization, transaction, and update. During the first phase, authorization, the user agent sends a username and a password in the clear, by the way, so no encryption, to authenticate the user. During the second phase, transaction, the user agent retrieves messages. Also during this phase, the user agent can mark messages for deletion. Also, he can remove deletion marks and obtain mail statistics, for example. The third phase, update, occurs after the client has issued the quit command, and by doing so, he will end the POP3 session. At this time, the mail server deletes the messages that were marked for deletion, if any. Next, we have IMAP, short for Internet Mail Access Protocol. It's way more complex, but it does solve some of the biggest POP3 issues. For example, with POP3, in our previous example, once Bob has downloaded his messages to the local machine, he can create, mail folders and move the downloaded messages into the folders such as inbox or some specific folders. Maybe he wants to filter the emails sent from maybe some specific companies or colleagues, or group mails by topic or projects or things like that. But then Bob can only locally move these messages, delete messages, and search for messages. So this is all happening locally on Bob's computer. Nowadays, we want to be able to access our mail inbox from different devices. So storing emails locally on one of the devices is not going to work, because obviously the emails we store on one computer, we are not going to be able to see on the other computer. Obviously, we would prefer to maintain our inbox on a remote server, on the mail server, that can be accessed from any computer or any device. This is not possible with POP3. The POP3 protocol does not provide any means for that. And with IMAP, this is enabled, and that is actually the main difference. Finally, with HTTP, or we can call it webmail, with this service, the user agent is an ordinary web browser, and the user communicates with its remote mailbox via HTTP protocol. When a recipient such as Bob wants to access a message in his mailbox, the email message is sent from Bob's mail server to Bob's browser using the HTTP protocol rather than the POP3 or IMAP protocol. When a sender, such as Alice, wants to send an email message, the email message is sent from her browser to her mail server over HTTP. But then Alice's mail server still sends messages to and receives messages from other mail servers using SMTP. And that's it for our lesson on email protocols. See you in the next one.
Let's look at DNS now, which is a very important application layer protocol. First, let's define it. DNS, which is short for the Domain Name System, is a hierarchical and distributed naming system for computers, services, and other resources connected to the internet. And basically what DNS is used for is to translate for us human-readable domain names, such as www.udemy.com, into the IP address, which, as you'll see later, is the only parameter a network device understands. For example, we need traffic to be routed through routers, and routers don't understand URLs. You have to tell them what IP address you want to go to. And I'll show you later how I found out what is Udemy's IP address. So how does it really work? First, the user using the web browser requests access to a web page. For this example, we'll use udemy.com. This is all the information the user enters, but the computer can't really do much with that because the computer needs an IP address, not the URL. So the computer sends out a DNS request to a DNS server, basically asking, hey, tell me where to find this website. What's its address? The DNS server either has this information stored in its database, or it needs to connect or contact another DNS server to find out. Either way, once it figures out where udemy.com resides, it will send a response. Now, the web client has all the information to complete the network packet, puts the IP address DNS server returned as the destination address, and sends the packet to that IP. Next, of course, if the client's request is correct and the server indeed has the requested page, it returns the HTTP response. And this was the very basis of DNS. Before we move on to another topic, let me show you some readily available tools that you can immediately test out on your computer. Disclaimer, I'm recording this on a PC which has a Windows on it, just because the recording tools are better here, but for Linux and Mac, the commands are rather similar and you'll be able to find them with a quick Google search. So you need to open Command Prompt, and that's where we'll be entering these commands. All right, so I have my command prompt window open here, and we're going to test our commands right now. We're going to start with nslookup, nasa.gov. nslookup is a basic command for requesting DNS records. There's several types of DNS records, but for our foundational networking needs right now, the only important one for you is the A type. You'll see it later in our DNS database. The A type is a simple mapping between a domain name and an IP address. So with this command, we're simply trying to get the IP address where nasa.gov resides. And we got 4 addresses. 2 of them are IP version 6, but for our foundational networking course, that's not the scope. So let's focus on the 2 IPv4 addresses here. Now, the first 2 lines of information we received are actually regarding our own local DNS server. So your computer has a small DNS server in it, and it has sort of a DNS cache, which we will look into later. By the way, if you were to use the ping command, it will also tell you the IP of the domain you're trying to ping, simply because in order to ping, you also need to find the IP address first. Computers can't ping websites, only IP addresses. But I believe NASA actually blocks pings, which is the ICMP protocol. Yeah, so the request is going to time out. But you can notice that we got the IP address here. It's the same IP address that was returned to us by the NSLOOKUP command. All right, we're going to try to ping another website. Let's try udemy.com. And we're getting the replies there, so all is good with the ping. Our other two commands, ipconfig/displaydns and ipconfig/flushdns. These two commands are more about your local DNS database. So ipconfig/displaydns will show you your local DNS cache. This is the place first checked when you want to go to a website. Your computer will first look there because it's faster to just get the IP from a local file than go request the answer from a remote server. So let's check out what's in my DNS database, ipconfig/displaydns, and we get lots of some just random domains here. Obviously, these are the ones that we tested out. Then I have lots of Kaspersky pings because I use their products on my computer. Lots of Microsoft stuff, which is also expected. Wow, lots of Kaspersky things. All right, so let's flush this cache. That's obviously what this command ipconfig/flushdns is for. It empties this cache in case maybe you run into an issue and want to update the DNS records, for example. So I'm just going to repeat the previous command and you will see that there's nothing in the cache right now. I also want to go to this record type thing. This is the A type we already mentioned, and then time to live is the time for which this record will be kept here locally, because these records do expire. Obviously, websites change their IPs sometimes, so you can't write these in stone. They must be checked with the DNS servers periodically. And now we have a simulation to look at. Again, it's in Cisco Packet Tracer, which is free, and the simulation file is in the resources section of this lesson on Udemy. So go download it if you want to play a bit more with it. Here's the simulation. We have a bunch of computers. We have a ton of different networks, but the devices and services that we're going to focus on here are this DNS server, and then these servers up here. The servers on the right hand side have a similar function. So they are an email server and a web server, but we don't have time here to go through all of them. So I really encourage you to download this simulation file and play with it a bit on your own. What I am going to do here is I'm going to open the simulation mode. I'm going to go to PC1. First, I need to check what is the domain of this server. So what is the URL I need to request? I'm going to go to DNS here and look at the mappings. As you can see in the type column, they are all A records. So I want to go to www.msn.com on my PC1 computer. So I'm going to go to desktop and open the web browser app. It takes a little while to open it. Here we go, www.msn.com, and I'm going to press go. So we have now requested that page, and initially the first packet that is created by this PC is the DNS packet. Let's open it to see what's inside. So obviously it starts at layer 7 because this is a layer 7 protocol. The DNS client sends a DNS query. So it sends an A, this is important, this is the type of the DNS query, to the DNS server. If we go to PDU details, we might see some more. So we are, can we see the request? Hold on. Yes, here it is. So this is the DNS query, name www.msn.com. And then this is the IP address of the server, probably. That's probably like configured on the computer PC1. Let's forward the packet further. It goes to the router, switch, and then finally it reaches the DNS server. The DNS server sends a response back and will open the packet now that it has reached PC1. The DNS client receives an DNS response. Again, let's look at the details. So we have both the query and the answer, and this time we have this IP field which tells us where this website resides. So this is its IP address. If we look at the second packet that just got created, it's the TCP request. It's the first out of the 3 TCP packets that are going to be sent out as part of the 3-way TCP handshake. Let's go further with it. So the connection is now being established, and with the final TCP acknowledgement, we are going to also send out the HTTP request. If you open the HTTP request, here it is. So that's our HTTP request. It's very similar to what we saw in the HTTP protocol example of the request. So this is what we are asking from the server. And then once the HTTP reply reaches the requester, PC1, let's go back to PC1. Voila, our page has opened. Obviously, this is not the original msn.com web page. I have edited it. It is a bit limited what you can create on these web servers as an HTTP page, but it's not bad for testing and simulating and learning. All right, I'm going to stop this simulation here, not to make this lesson too long, but again, please download this file and play with it a bit more on your own. See you in the next lesson.
Today we talk remote access. We'll cover why do we even need remote access. We'll cover Telnet and SSH as some of the most used options. And we'll look at a practical example for those of you who maybe never used these tools. First of all, why do we need remote access at all? If you're cybersecurity minded as I am, you'll see pretty quickly that remote access will always be one of your weak links. Well, if your company's mode of work is mostly or entirely remotely, you'll need a good and stable setup for employees to access the resources they need for their work on a constant basis. Second, you might be working from an office, but your IT assets are locked up in a data center and you might not even be allowed to physically access it. Also, no matter how good of an expert you might be, you're likely to need some sort of support for your IT or network devices. Oftentimes, support will want to connect remotely in case of urgent incidents that require an immediate intervention. So let's talk about our options. Here, we're talking specifically about the tools used for computer network administration. I know you've probably heard of or used TeamViewer or RDP. But these protocols here, Telnet and SSH, are for accessing a device via a terminal. All right, now let's dive into the main differences between Telnet and SSH. Firstly, Telnet is also referred to as VTY, short for virtual teletype. It's the more simple option and is therefore, of course, easier to configure. It uses TCP and the default port is 23. And then the most important thing to note is that while it does support authentication in the form of a username and password, those are transferred between the client and the server in clear text. So watch out. Just to clarify here, the access can be established between two equal devices, meaning two servers, for example, or two routers. The client side is not a computer and the server is an actual server, like in HTTP. There can be a client that is the same as the server, meaning the same type of device, but the client here is referred to as a device that is requesting the access and the server is the one being accessed, to put it that way. Okay, we'll see how that works in practice soon. Just for the sake of comparison, SSH is Telnet's alternative. It's short for Secure Shell. It also uses TCP, but port 22. It's also a client-server protocol with the same logic as Telnet as to who's client and who's the server. But here comes the main difference. Authentication between client and server is encrypted, and specifically it uses public key encryption, and the same goes for data transfer. All right, now let's go to the simulation. All right, my goal here is to simply show you what it looks like. So this is going to be short. We are going to try to remotely access this router right here, router C, and just to get the traffic going, and so that that's successful, we're going to send one ping for starters. And then I am going to look at some of the IP addresses of this router. Let's use 10201 because that's the first IP address I see here. So 10201, and I can see here my credentials that I have pre-configured here on this router. I'm going to open computer X, that's my username too. I'm going to go to command prompt and I'm simply going to type in telnet 10201. What was it? I already forgot the IP address. 10201. All right. Press enter. And then I've already accessed this router. So this prompt right here that I'm getting, that's the router asking me for the credentials. If the connection was not successful, meaning something's wrong with the routing in between, I would get a completely different message, but this is so far working as expected. Username is X, and then I'm going to type in cyberquince. You can see that here. And voila, I've accessed the router. Now I can go into enable mode. Enable mode also has a password. I believe it's the same one, so cyberquince. All right, with access. And from here, I can, change the router's configuration. If I were an administrator working at a company that is taking care of this router, I would just be doing my job basically by configuring this router. Let's just issue a simple command to see how it's working. It works very well. Actually, you can see here the configuration that I had to type in to be able to access it via Telnet. All right, that would be it for this very short simulation. Hope you found it useful and see you in our next lesson.
In this lesson, we make an introduction to the transport layer and its services. So, a transport layer protocol provides for a logical communication between applications running on different hosts. By logical communication, we mean that from an application's perspective, it is as if the hosts running the applications were directly connected. In reality, the hosts may be on opposite sides of the planet, connected via numerous routers and a wide range of link types. In this architecture here, we have a ton of links, connections, devices, etc. And the real internet is even many thousands more time complex than this. However, from the perspective of the transport layer, if this computer up here in the upper left corner wanted to send a message to a faraway computer that's on the other end of the world, perhaps, from the perspective of that application, the receiver is just next door. So, to conclude, application processes use the logical communication provided by the transport layer to send messages to each other, free from the worry of the details of the physical infrastructure used to carry these messages. I already hinted that the internet and more generally a TCP/IP network makes two distinct transport layer protocols available to the application layer. One of these protocols is UDP, short for User Datagram Protocol, which provides an unreliable, connectionless service. The second of these protocols is TCP, short for Transmission Control Protocol, which provides a reliable, connection-oriented service. When designing a network application, the application developer must specify one of these two transport protocols. Now, we'll talk about the network layer later, but for now, I will spoil for you this much. The Internet Protocol, IP, that resides on the network layer and that we all currently use, provides the best effort service. This means that IP makes its best effort to deliver segments between communicating hosts, but it makes no guarantees. In particular, it does not guarantee that the packet will at all be delivered. It does not guarantee orderly delivery of packets, and it does not guarantee the integrity of the data in the packets. For these reasons, IP is said to be an unreliable service. So, the most fundamental responsibility of UDP and TCP is to extend IP's delivery service between two end systems to a delivery service between two processes running on the end systems. And, if needed, to also improve that best effort promise by using TCP. That's it for an introduction. Let's now talk about TCP and UDP details. All right, let's start with UDP. UDP, defined in RFC 768, does just about as little as a transport protocol can do. Aside from some light error checking, it adds nothing to IP. In fact, if the application developer chooses UDP instead of TCP, then the application is almost directly talking with IP. UDP takes messages from the application process, attaches source and destination port fields, adds two other small fields, and passes the resulting segment to the network layer. The network layer encapsulates the transport layer segment into an IP datagram and then makes a best effort attempt to deliver the segment to the receiving host. If the segment arrives at the receiving host, UDP uses the destination port number to deliver the segment's data to the correct application process. Note that with UDP, there is no handshaking between sending and receiving transport layer entities before sending a segment. For this reason, UDP is said to be connectionless. Now, you might be wondering why an application developer would ever choose to build an application over UDP rather than over TCP. Isn't TCP always preferable since TCP provides a reliable data transfer service while UDP does not? Well, the answer is no, as many applications are better suited for UDP for the following reasons. First of all, under UDP, as soon as an application process passes data to UDP, UDP will package the data inside a simple UDP segment and immediately pass the segment to the network layer. TCP, on the other hand, has a congestion control mechanism that throttles the transport layer TCP sender when one or more links between the source and destination hosts become congested, plus some other mechanisms that we'll discuss in more detail later. But all of these means that the application has less control over when the message is sent if it uses TCP. Second, as we'll discuss later, TCP uses a three-way handshake before it starts to transfer data. UDP just blasts away without any formal preliminaries. Thus, UDP does not introduce any delay to establish a connection, again, saving time. No connection state. This is another TCP functionality. Basically, TCP maintains a connection state in the end systems, and that, of course, you guessed it, also adds delay. Fourth, small packet header overhead. You saw in the previous example that UDP only adds 4 fields to the actual message, and you'll witness soon how much more TCP adds, therefore making the packet bigger, and with that, of course, also more difficult to get across a network. Before we go any further, I mentioned in the previous slide that UDP only adds 4 fields to the application's message, so let's look at those 4 fields. It's rather simple, actually. There's the source number, which identifies the sender process, destination port number, which identifies the application which should receive the message. For example, if it's HTTP, then the port number would be 80. But of course, HTTP doesn't use UDP. This was just for the sake of the example. And the other 2 fields tell us the length, which is the number of bytes in the UDP segment, including both data and the header. And the checksum is used by the receiving host to check whether errors have been introduced into the segment, but bear in mind that this is a very simple control. TCP has many more mechanisms for ensuring error identification and correction. Finally, let's look at some examples of heavily used applications nowadays and which transport protocol they use. First of all, email, of course, uses TCP because obviously you want the sent email message to arrive in the same format and with the same content that it was sent with. Web surfing, it's the same. You don't want to be reading an article, for example, and be missing 1 or 2 paragraphs or some pictures, which could easily happen with UDP. File transfer, obviously for the same reasons, uses TCP because if a file is not transferred in its entirety, then you might have issues running it or seeing it or whatever else. I mean, you want your file in its complete state in the way that it was sent. But streaming services mostly use UDP. Sometimes there are TCP-based streaming services, but mostly they use UDP. VoIP, also we used it as an example in one of our previous lessons. It uses UDP. And the reason is the same for all of these 4 applications here. Basically, UDP will transfer as many messages as possible in the real time. And then if we look at streaming, for example, you're receiving a certain amount of frames per second. If a few frames go missing, you're still going to get the context of the streaming material you are watching. Let's say you are watching a movie. You would rather be missing some of the frames than receive those frames like 5 minutes later or something like that, when it absolutely doesn't make sense to even see them. Your human eye is most likely not going to notice several frames missing. Routing almost always uses UDP. We'll talk about routing some more later. And then real-time gaming, for the same reasons I mentioned for streaming and VoIP, typically uses UDP. And that would actually be it regarding UDP. Next, we are going to talk about TCP some more.
Before we head on over to TCP, I want to show you how this checksum control works. First off, a short intro. The UDP checksum provides for error detection. That is, the checksum is used to determine whether bits within the UDP segment have been altered, for example, by noise in the links, or while stored in a router as it moved from source to destination. Okay, on to the example. Let's suppose that we have these 3 16-bit words. The sum of the first 2 is this, the number below the line. And the way we got this number is simply converting the first 2 to decimal, adding them up and converting back to binary, or at least that's how you can test this result on your own. If you add the third number to this sum, you get the number on the screen. This time we have overflow, so that is wrapped around. Now what we need is a so-called complement, which is simply put ones turned into zeros and zeros into ones. And this is that number. That actually is our checksum. Note that at the receiver, all 4-bit words are added, including the checksum. If no errors are introduced into the packet, then clearly the sum at the receiver will be all ones. If one of the bits is a 0, then we know that errors have been introduced into the packet. And yeah, that's the UDP checksum for you, a rather simple concept. See you in the next lesson.
In this lesson, we finally tackle the topic of TCP. In essence, TCP is a reliable data transfer protocol that is implemented on top of an unreliable end-to-end network layer. We already mentioned that the network layer does not guarantee, well, basically anything other than trying the best it can to deliver our packets. But how does TCP change that? Let's start from comparing UDP headers with TCP headers. I mean, based on this slide, need I say more? Now, on the serious note, the UDP one is on the left. It has only 4 fields. And TCP, well, TCP has plenty. And note that one tick mark represents 1 bit position in these pictures. By the way, these are screenshots of the original RFC documents for UDP and TCP protocols respectively, and here are the links to them. All right, enough with the chit-chat. Let me show you what all of these fields actually bring to TCP and how it all works. First and foremost, the three-way handshake. We mentioned already that TCP is called the Connection-Oriented Transport Protocol. Well, the three-way handshake is a process used to establish a connection between a client and a server. It uses synchronize acknowledgement, and acknowledgement packets to make that happen. How does that exactly work? As a first step, the client initiates a connection with a server. It sends a packet with SYN, which is short for synchronize, and it sets a so-called sequence number, which is random. Let's say that in our case, that's 1010, so 1010. The sequence number indicates the beginning of the sequence for the data our client wants to transmit. In second step, the server responds with its sequence number, which is unrelated to the client's number. However, the ACK, short for acknowledgement, is very much related to the client's SYN number because it is incremented exactly by 1. This way, the server acknowledges that it has received the previous sequence and it is now expecting the next sequence, which is equal to previous sequence plus 1. Finally, our client responds to the server by sending the acknowledgement number that is now the server's sequence number incremented by 1, and voila, the TCP connection is established. But now what? Well, now we want to transmit data. TCP offers a service where it recovers data that is damaged, lost, duplicated, or delivered out of order by the internet. TCP achieves this reliability by assigning a sequence number to each octet it transmits and requiring a positive acknowledgement, ACK, from the receiving TCP. Let's look at some examples. Let's take this scenario in which host A sends one segment to host B. Suppose that this segment has sequence number 92 and contains 8 bytes of data. After sending this segment, host A waits for a segment from B with acknowledgement number 100. Now, although the segment from A is received at B, the acknowledgement from B to A gets lost. In this case, the so-called timeout event occurs and host A transmits the same segment. Of course, when host B receives the retransmission, it observes from the sequence number that the segment contains data that has already been received. Thus, TCP in host B will discard the bytes in the retransmitted segment. In a second scenario, host A sends 2 segments back to back. The first segment has sequence number 92 and 8 bytes of data, and the second segment has sequence number 100 and 20 bytes of data. Suppose that both segments arrive intact at B, and B sends 2 separate acknowledgements for each of these segments. The first of these acknowledgements has acknowledgement number 100. The second has acknowledgement number 120. Now suppose that neither of the acknowledgements arrives at host A before the timeout. When the timeout event occurs, host A resends the first segment with sequence number 92 and restarts the timer. As long as the ACK, or the acknowledgement for the second segment, arrives before the new timeout, the second segment will not be retransmitted. Finally, a third scenario, just to get our exercise in and really understand how this works. Let's suppose that host A sends the two segments exactly as in the second example. The acknowledgement of the first segment is lost in the network, but just before the timeout event, host A receives an acknowledgement with acknowledgement number 120. Host A therefore knows that host B has received everything up through byte 119, so host A does not resend either of the two segments. Finally, we can't finish this lesson without mentioning congestion control as an important TCP mechanism. It uses, or TCP uses a reactive congestion avoidance algorithm that dynamically adjusts the rate at which data is sent to reduce the amount of network congestion and packet loss. What does that really mean? Well, congestion control uses the slow start algorithm to help control network congestion by slowly introducing packets to the network when an application is started. The slow start algorithm has a threshold defined by a formula, and we'll look at that next, but for now, just bear with me. So there's a threshold, and after that threshold is passed, we move it into a congestion avoidance phase. And then there's a threshold for that phase too. And then once that one is surpassed, we move into congestion detection phase. This is what that looks like. Now, MSS is short for maximum segment size, or in plain English, it's the size of our packets that is represented on the vertical axis. The horizontal axis represents time, so the passing of the time. Well, the basic idea is this. Initially, the computer starts sending packets slowly. It monitors how and if the acknowledgements are coming back. If they're coming back as expected, that tells us that our packets are not getting dropped and everything is fine with the network. So we start sending our packets just a bit faster. As we reach this first threshold where some of our packets start failing, we gently keep increasing the size of our packets. And as time goes by and we find that sweet spot or the ideal size of the packets we should send, we simply continue to send that size. And because I don't want to overwhelm you with this one lesson, we'll stop here and then talk about the TCP header in a separate video. See you there. As promised, here we focus entirely on the TCP header. Now, as with UDP, the header includes source and destination port numbers, which are used for sending the transferred data from and to upper layer applications. Also, as with UDP, the header includes a checksum field and the function is the same. But other than those, there's the 32-bit sequence number field and the 32-bit acknowledgement number field. Those are used by the TCP sender and receiver in implementing a reliable data transfer service, as we discussed in the previous lesson. Then there's the 16-bit receive window field used for flow control. Basically, it's the number of bytes that a receiver is willing to accept. Next, header length field specifies the length of the TCP header in 32-bit words. The reason why the TCP header can be of a variable length is because of the TCP options field. Now that field, the options field, is optional and is of variable length. It's used when a sender and receiver negotiate the maximum segment size, or MSS, from our previous presentation, or as a window scaling factor for use in high-speed networks. Then the flag field contains 6 bits. The ACK, or acknowledgement bit, is used to indicate that the value carried in the acknowledgement field is valid. That is, the segment contains an acknowledgement for a segment that has been successfully received. The RST, SYN, and FIN bits are used for connection setup and teardown, and setting the PSH bit indicates that the receiver should pass the data to the upper layer immediately if possible. Finally, the URG field, or the URG bit, is used to indicate that there is data in this segment that the sending side marked as urgent, or the sending location thought is urgent for the receiver to receive as soon as possible. And the location of the last byte of this urgent data is indicated by the 16-bit urgent data pointer field. TCP must inform the receiving side when urgent data exists and pass it a pointer to the end of the urgent data. Now, in practice, PSH, URG, and together with them, of course, the urgent data pointer as well, are usually not used, but I mentioned it here just so you know what they're for. Oh, and I almost skipped padding. Padding is there to ensure that the TCP header ends and data begins on a 32-bit boundary. That field is composed of zeros. Basically, the TCP process will just add enough zeros to reach the 32-bit number. All right, hopefully that was clear for you. If you have any questions, don't hesitate to ask in the Q&A section. Finally, we've made it to the network layer. Let's get into it right away. Remember how we said that the transport layer is all about application to application and that it doesn't really need to be concerned with what's underneath it? Well, the network layer is very much concerned and about a lot of things. The main two of those things are the IP address and the routing. Both of those topics are covered in this section, but first, I want to spend a few moments discussing the most important device related to this layer, the router. What is a router? How is it different from a switch? And what do we future network engineers and/or administrators have to do with routers? Well, per Wikipedia, a router is a networking device that forwards data packets between computer networks. Routers perform the traffic directing functions on the internet. Sounds very important, right? Let's see how routers do that. Well, each router has what is called a routing table. The network layer must determine the route or a path taken by packets as they flow from sender to receiver. Information that helps the router make those decisions is called a route. And what we see in this screenshot here is a routing table filled with routes. Each line is one route. Let's take an example to look into. Let's look at this second line here, 10.10.10/24. For now, we're going to focus on the IP address, which is this number 10.10.10, and the column on the far right titled netif. Netif is short for network interface, and that tells us where the network 10.10.10 is connected. Here's a visual. Here we have a depiction of three networks. There's network 1 on the left, 2 in the middle, and 3 on the right. The three networks are separated by routers, as that's usually the case in real life too. Anyway, each router, let's call them left and right routers, has its own routing table. The routing table is an address book of routes from the perspective of that router. So for example, router on the left knows that network 1 is connected to its interface E0, and you can see which interface that is here. Also, there's this metric value, which tells us how far away that network is. Now, there's many ways to measure these metric values, but in this case, 0 means that the network is directly connected to the router where we found this routing table. If we look at the third row, that route points to network 3. Network 3 is this network on the right here. And if a router on the left receives a packet that wants to go to network 3, it will send it out interface S0. S is for serial, by the way. Let's take another example. Let's say that computer 3.1, that's this computer's IP address here. It's obviously not complete, but for the sake of simplicity, let's call it 3.1. And that computer wants to send a message to computer 1.2 on the left. It will create a packet, put its IP address 3.1 as source IP, put 1.2 as destination IP, and send the packet out. When the packet reaches router on the right looks at packet's destination IP, looks at its routing table, and voila, the first entry says where network 1 is. The router sends this packet through interface S0, then the packet gets to the router on the left, and the router on the left has the same network in its routing table too, and its routing table says to send this packet out interface E0, and that's what the router does. Next, the packet reaches a switch, and switches are more of local devices, so there is no routing there. The switch knows where the computer is, sends the packet out that interface, and the packet reaches its final destination. And yeah, that would be the gist of it. I suggest to spend some time on the previous slide and make up some scenarios of your own to practice. And as always, if you run into something that's unclear, please ask the question in our Q&A section.
In this lesson, we talk about the IP address. First off, let's see what kind of addressing is there in a computer network. On the first 3 layers, there's not really any addressing going on, it's just processes. On the transport layer, there's ports, and those already are some sort of addressing. On the network layer, finally, there's the IP address, which we are interested in today. But let's see the rest. Layer 2 gives us the MAC address, and unlike the IP address, which is considered a logical one, MAC is a physical address, meaning it can't be changed, or let me correct that, it can't be and shouldn't be easily changed. Its purpose is different than that of the network layer address. We'll discuss that next. In essence, Internet Protocol, what IP is short for, is the Internet layer. All other protocols we mentioned exist on the physical data link and network layer are there solely to support the Internet Protocol. Now, what's an Internet Protocol address? Simply put, an IP address is an identifier. It uniquely identifies a device inside a network at a given moment. Why do I say that? Well, devices can easily change their IP addresses. One important thing to know is what an IP address actually looks like. Here's an example. In binary format, this number here has 32 bits. It is separated in 4 sections called octets or bytes. And obviously, if you divide 32 by 4, you'll notice that each octet has 8 bits. Here's the IP address from our previous slide. Let's see what it looks like in binary format. Don't worry, I'll explain a bit how we got here, but if you need to know the details, please go to my IP addressing and subnetting 0 to Hero course here on Udemy. Send me a message to get it for free. There's plenty of examples focused on just this topic there. All right, now let's quickly review this number here. In every binary number, we start from the right. The number furthest on the right will always have a value of 1. The one on its left-hand side will have the value 2. Next one will be 4. Next one will be 8. Next one, 16. Next up is 32. 64, and finally 128. It's important to remember that this rule applies to each one of the octets individually, so the next octet also holds same values for each position, this one as well, and fourth octet does too. And now what I'm going to do is I'm going to just leave the numbers where in the binary number there are ones and remove the numbers under zeros. Now you can probably guess what we do next. Yep, we just sum up the remaining numbers. For the first octet, 64 plus 4 plus 2 plus 1 equals 71. Second octet sums up to 205, 205. In the third octet, obviously, we have 0 as there is nothing to sum up. And finally, in the fourth octet, that one's easy. It's 8 plus 4 plus 1. In total, that's 13. And now one last thing, I promise. If all of the bits were ones and we sum up all 8 of those bits, just like we did previously, what number do we get? The total would be 255. So for now, just know that if you were to see this IP address somewhere, it's a legitimate one. In binary, that would be this number. So I want you to focus on the second octet, which is entirely filled with ones. With this, I just wanted to practically explain why you can't have an IP address of, let's say, 71.256 or a number higher than that in any of the octets. Just keep that in mind, okay? And with that, we're through with our IP address lesson. Bye. Now that we've learned about IP addresses and their format, let's investigate just a tiny bit further. Again, there's an entire course on this topic on my Udemy channel. If you want it for free, send me a direct message and I'll try to generate a coupon for you. All right, let's go to the basics. First, let's discuss the parts or segments of an IP address. No, I don't mean octets, which we already mentioned, but this, the so-called network part and the host part. Let me explain it to you in a practical example. You already saw this topology in our OSI model example, only this time I added some labels to better visualize the networks in it. To make sure it is clear, all of these labels that display 10 dot something, 10.1, 10.10, 10.11, etc., represent the network ID or a network IP address. And we're about to explain what that means, but just keep in mind that none of these are assigned to any of the devices you see in this picture, the routers and the computers. They are all network ID numbers. So what do all these numbers here have in common? Well, for starters, they all start with 10, and it's always their second octet that differs. What if I also told you that these are the individual IP addresses assigned to each device? Just to clarify, for example, 10.1.0.1 is assigned to the interface of router A, 10.1.0.2 is assigned to PCX. Next, for example, 10.12.0.1 is assigned to this interface on the right of router 1, and 10.10.0.2 is assigned on the left interface of router 1. And you'll notice very quickly that this time only the fourth octet changes, and in particular, we're trying to use the numbers consecutively, meaning in the networks where we have two devices, we'll assign the first with .1 and the second with .2. They won't be some arbitrary numbers. And that's because as a network administrator, you usually want to save IP addresses. All right, let's move on. Back to our IP address example, 71.205.0.13, where the first three octets belong to the network part and only the last, fourth octet, belongs to the host part. In practice, this is what that means. If we were to have a network scenario, like in this picture, we could only change the fourth octet and allocate IPs in this network that all begin with 71.205.0. In other words, the first three octets must always be the same. That's the network part. And then, if we were to add another network to our router, that other network can not have the same network ID, meaning the first three octets must be different from the existing network 71.205.0. Okay, this was all practical examples. Let's go back to the numbers. How do we know which is which part in an address? Well, there's this thing called network mask. And what is a network mask? Per definition, a network, or otherwise called a subnet mask, is a 32-bit number created by setting host bits to all zeros and setting network bits to all ones. And now you're probably even more confused, but don't give up just yet. We'll explain it using our example again. So each IP address, or at least each IP version 4 address, has 32 bits. Let's turn this IP into bits again. The mask masks the network part of the address. Try to remember it like that. So the exact number of bits in an address that represent the network part will have the value of 1, and the host's part will have the value of 2. And so this second number that appeared in the second line is the mask. And if you count the number of ones in the mask, just count, not summarize by converting to decimal, you'll get, in this case, 24 bits. So that's why /24. Let's look at another example with a different mask length. Let's use the same IP address, but with a mask of /16 this time. That means that only the first 2 octets will represent the network part, and we'll have more space to allocate to the hosts now. By the way, 1 octet has 8 bits. So yes, I'm picking easy masks on purpose here, as it gets a bit more complex if you try to customize that. And again, if you want to know how that works, I've explained it with detail and many practical examples in my other course, which again, if you ask for a free enrollment, I'll send you a coupon. But now let's work with this new /16 mask. This is what the binary format looks like. This is the IP address, and this is the mask. All right, one more thing, I promise. This IP, 71.205.0.13, with both of the masks we've used so far, 16 and 24, can only be allocated to some host, such as a computer or server or maybe a router interface, but that IP can't be the network ID address. Why? Well, there's two special addresses in these subnet ranges. The first special address is the network ID address. That is the first logical IP that you'll get by copying all the bits from the network part and filling the host part with zeros. I'll add it down here. So we took 71.205, that's our network part, and then instead of 0.13, we used all zeros in the host part, and sure thing, we'll get zeros in decimal too. And now the second special address is the broadcast IP. That's the IP address a computer will use as a destination address in a packet if it wants all the computers in that network segment to receive that packet. For example, this broadcast IP is used in DHCP protocol once a host starts searching for the DHCP server and initially doesn't know where the server is or the server's IP address. So it sends out this packet to everybody it can reach with hopes that some of them responds, "Hey, I'm a DHCP server, talk to me." And the way we get this broadcast IP is just like with the network ID. Here we also copy the network part bits verbatim, and then we fill the hosts part with ones. And we already spoke about what that is in decimal. 81 bits make a total of 255 in decimal. Now, if you're wondering, can we have 255 in the first octet, for example, and then some other numbers in other octets? Yes, we can. An IP address can start with 255. You can't have an IP start with a 0, though. So try to remember that. And that's it for this lesson. See you in the next one. Bye! In this lesson, we talk about another important network protocol, DHCP. Per definition, DHCP, short for Dynamic Host Configuration Protocol, is a network management protocol and is used for automatic assignment of IP addresses, but also some other parameters as well. For example, it will not only tell a computer what its IP address should be, but on top of that, it can also set the default gateway IP address, tell the computer what its DNS server is, etc. Also, important note, DHCP uses the client-server architecture. And now we're about to see how it works exactly. In essence, DHCP exists so that network administrators don't have to manually configure IP addresses on the devices connected to a network. Instead, you can configure the device to use DHCP to get its own address. And once you do that, the following happens. First, let's say that the computer in this picture, client, was just now switched on. It doesn't have an IP address, a network mask. It doesn't know its DNS server's IP, it's all blank. If it's configured to use DHCP, what it will do is it will send out a broadcast packet, because again, it doesn't know the DHCP server's IP address, and the packet will go to every device in that local area network. One of the hosts in the network must be configured as a DHCP server, and by the way, it doesn't have to be a real physical server. DHCP is just a service that you can start on a laptop as well, or on a router, for example, which is actually used quite often, DHCP server configured on a router. Anyway, whoops, let's go back real quick. Anyway, the client sends out the DHCP discover message. The server receives it and it sends back a so-called DHCP offer. It usually contains the set of IP parameters, one of which, the most important one, of course, is the IP address for the client itself. It's usually the next IP or the first available IP address from the DHCP pool. Basically, the server is offering the IP parameters to the client. This is due to the fact that the client might reach several DHCP servers who might send offers at the same time. Anyways, the client responds with a request, formally requesting the offered parameters. DHCP server accepts the request with an acknowledgement, and voila, our client receives its IP parameters. And let's stop right here. This is all the information you'll need for the computer networking basics. We continue learning in the following lessons. So see you there. We've already mentioned and used the ping, but we haven't touched upon ICMP. ICMP, short for Internet Control Message Protocol, is, as the name suggests, another network layer protocol that the ping is only a part of. Or in other words, ping is one of the ICMP tools, if you will. It's used to diagnose network issues. Let's look at all three real quick. We'll start from traceroute. First, what is it? It's a tool used to display the physical routing path from device A to device B. Device A presumably being you, the network administrator, initiating the traceroute, and device B being the target of the traceroute. Basically, it maps out the hops that a packet traverses to get to the target or destination. Let's call it that. Target sounds a bit, you know. Also, if you are a network admin and you notice some link doesn't work, traceroute will help you understand exactly where or at which hop the issue resides. Here on the slide, you can find the commands. Try to do it from your terminal for homework, let's say. Okay, next, let's touch up on ping, the star of the show here. So ping is actually simpler than traceroute. Its whole point is to send out a packet and wait for it to return. In the process, it also measures the time that passes by, and information that can help an administrator understand if there's any issues with the link he or she is testing. And finally, we have error reporting. Network equipment manufacturers are known for implementing the ICMP protocol to periodically test connectivity and report on issues once they're detected. Also, ICMP is used in situations where packets are rejected. For example, if one device sends a packet that is over the limit in size allowed on that link, the device that decides to reject that packet will inform the sender exactly by using the ICMP protocol. And that's all well and nice if it weren't for the bad guys. ICMP is known to be used in DDoS attacks. If you're not familiar, distributed DOS or DDoS attacks are the attacks where hackers overwhelm the target with unwanted traffic, so the target cannot provide service to its legitimate users. There are multiple ways an attacker can use ICMP to execute these attacks, including the following. There's the ping of death attack. Here, the hacker sends an IP packet that's larger than the number of bytes allowed by Internet Protocol. On the way to its intended destination, the oversized packet is fragmented. However, when the recipient device reassembles the packet, the size exceeds the limit, causing a buffer overflow, and the receiving machine is frozen or it crashes. Next, there's the Smurf attack. In a Smurf attack, the attacker sends an ICMP packet with a spoofed source IP address, and the network layer equipment replies to the packet, sending the spoofed address a flood of packets. Like the ping of death, Smurf attacks are more likely to work on undefended legacy, or in other words, old network equipment. And finally, we have ICMP flood attack. Sometimes it's called a ping flood attack. So the goal of this attack is to overwhelm the target device with echo request packets. Each echo request packet must be processed by the target and responded to with echo reply messages. This basically sucks up all the target computer's resources, and it causes a denial of service to any other legitimate users of that target, again, device, whether it's a computer or a server. So usually it's the servers that are targets of DDoS attacks. And with that, we're done with ICMP. Hope you found it useful. If there's anything left unclear, please reach out to me and other students in this course's Q&A section. See you in the next lesson. Now that we have covered a lot of the IP addressing, I want to talk about NAT. NAT, short for Network Address Translation, is a way to map multiple local private addresses to one or several, but preferably one public address. Why do we even need this? Well, the address space is limited. With the 32 bits, which is the exact length of an IP address, it gives us 2 to the power of 32 different unique combinations. In total, that's this number, which is a little over 4 billion. Now, do you think that's enough for today's size of the internet? Even though it sounds like a lot of numbers, with all these interconnected devices where each one needs a unique identifier, that is a unique IP address? Of course not. So how do we solve that? First, let's explore this private and public IP concept. In essence, there are 3 ranges that we call private, and these addresses are not allowed on the public internet. They can only be used within local area networks, or in short, LANs. The reason we were able to do that is due to the simple fact that normal personal computers don't need to be reachable by the public internet, meaning other remote users. While the servers that run applications, websites, and other services are likely to make sense to be available to, well, often everyone. What is shown on this topology here in the picture are 2 LANs, that's the networks in the circles, Obviously, it's all computers in there, and of course, there's tens, if not hundreds of thousands of such networks out there in the world. But there are far fewer networks like this small one up here, the two servers connected to a switch. The switch is named DC for data center because servers usually live in data centers. All right, so if we were to use NAT, this is the addressing that would be available for us. The two LAN networks could actually use the same IP ranges. So that's the green labels of IP addresses that you can see next to the PCs in these two LANs. And this is why, because we can have public IP addresses on the outside side of the routers. So let's use this to examine a scenario. Let's say that PC2, the one on the left, sends a packet to server 1. And this is how NAT works in the background here. This packet, while it was inside the LAN network, had a source IP address that we see under PC2. That's 10.0.0.3. Once it crosses router 1, its source IP changes from 10.0.0.3 to router 1's public IP address 173.0.11.2, and it keeps that IP as long as it's out there on the public web. So for example, let's say we open that packet while it's sitting on server 1. Its source IP would be 173.0.11.2, even though the source of that packet was 10.0.0.3. And once it returns back to the LAN, router 1 will look into its archive of translated IP addresses and find which private IP address was replaced by the public one for each particular request. Then it is switched back to the private one as the response packets come back into the LAN. This way, many local area network devices can use only one IP address. In our case, that's those two public IP addresses on the public side of our routers. But the important thing is that the important thing to remember is that there should be fewer public IPs than the private ones. That way, we're really saving IP addresses, or in other words, we're using less unique addresses. All right, that was your basics in network address translation. We continue learning in the next lesson, so see you there. Let's touch upon IPv6 a little bit, shall we? We mentioned in our previous lesson, where we learned about NAT, that there's not enough IP addresses to satisfy the needs of the world's internet. And NAT is one of the solutions for that. However, there's one more solution, and that's an improved internet protocol. The IP addressing system we described earlier is called the IP version 4, and the newer, improved one is IP version 6. First, an important statistic. We calculated that with IPv4, we used 32 bits, and that gives us a little over 4 billion unique IPs. With IPv6, we use 128 bits, which is 2 to the power of 128, which is this number. And that's a lot, right? Okay, so this is what an IPv6 address looks like. Let's take that apart to better understand it. First off, it's obviously written in a different format than IPv4's, in hexadecimal, and if this looked a bit long and chaotic, let me disappoint you some more. This is a shortened version of an IPv6 address, and that's what we'll dissect now. So first, there's 8 of these groups, and each group consists of 16 bits. The groups are, as you can see here, separated by colons. So if there are 8 groups, we should be able to count that many, right? Actually, no, because IPv6 addresses are so long, there are some rules you can follow to correctly compress the address. Let's count the groups we can see here. 1, 2, 3, 4, 5, and 6. And the missing 2 are here. Hidden or redacted because when you see 2 consecutive colons in an IPv6 address, that means that originally there was just zeros there. So let's define a rule here. If an IPv6 address contains 1 or more consecutive groups of zeros, they can be replaced by a double colon. Here's one more example. This is the full address, and this would be the shorter format. However, there's more opportunities to redact, so let's look at that. Using our first example, let's look at one of the groups in more detail. This one, the second group. We said that there's 8 groups, and each group holds 16 bits. 1 hexadecimal character is 4 bits, therefore there should be 4 characters in each group, but in this group there's only 3. Where did the 4th character go? Actually, it's not the 4th that's missing, but the 1st. And that is another rule for us to write down. Omit leading zeros in any group of 4 hexadecimal digits. The rule applies only to leading zeros and no trailing zeros. Even if a group consists of 4 zeros, we can only omit the leading 3. Let's look at another example. We have here the full IP address, and I've just now highlighted all the zeros that can be redacted. The 2 zeros in the first group can't be shortened. That's just a rule. All right, let's see what the address looks like shortened. Here it is. Let's imagine you as a network engineer see this somewhere and need to understand what was the full address. We'll start from the first group. There's 4 characters, so that one's complete. Next one has only 3 characters. That means that 1 leading zero has been omitted. Next, there's 2 characters in the group. That means that 2 leading zeros are missing. And eventually, we reach this double colon here. But in order to know just how many zeros were omitted there, we need to look at the rest of the address. And our final group is 3 characters, which means only 1 zero is missing. And back to the double colons, we counted 4 groups that we analyzed and reversed back to the full format. So with 4, we can see it means that another 4 are missing, because in total there's 8 groups in every IPv6 address. That brings us to the conclusion that this is what's hidden behind those 2 colons, because as we already defined, only consecutive zeros can be omitted like this. Now, you might wonder, what if there's consecutive zeros in multiple places in the address? Let's take this IP as an example. We have consecutive zeros in 2 places here. And this is a perfect time to introduce another and final, don't worry, rule for shortening IPv6 addresses. Replacement of consecutive zeros can only be applied once, because otherwise the original IPv6 address cannot be recreated from the shortened representation. In other words, we can only do this or this. Both are valid, by the way. This is not allowed, replacing both groups of zeros with double colons. All right, other than that, the subnet mask, allocating addresses, etc., is pretty similar to IPv4, or at least the logic is almost the same. So we're going to stop right here. See you in the next lesson. In this lesson, we learn about routing. I have prepared a practical example for you, again, in the Cisco simulator, but first let's discuss the basics. Let's say we have set up a new network and now we want to enable the communication between our devices. Obviously, if the network consists of more than 2 network devices, we are likely to need routing. Our 2 main options when talking about routing are static routing and dynamic routing. The basic difference is that with static routing, the network administrator needs to configure everything by hand. Now, in a small network, that might be perfectly doable, as you'll see in our simulator example. However, as soon as the network grows, and even if it grows just a little bit, configuring routes manually becomes very, very difficult. Now, since the routes are all written by a human, and humans make mistakes, it's more likely to experience configuration errors than it is with protocols. Next, although you can set up several different paths for each sender-receiver pair, this is extremely difficult to administer. That is why with static routes, there's usually only one for each destination. With dynamic routing, this truly isn't an issue, as routing algorithms will find and maintain redundant paths automatically. Finally, as a last point under static routing, in theory, it is more secure, but just because on the other side of the fence with routing protocols, in order for the routers to fill their routing tables, the routers will periodically exchange entire routing information, which, of course, if breached, you can imagine is a gold mine for hackers. However, in large systems, a human error in static routing could be as costly as that one security flaw of routing protocols. On the other side, we have dynamic routing. And here, the main point is that dynamic routing is enabled by different protocols and algorithms. These are developed to automate what administrators do manually with static routing. Obviously, they are far easier to configure, which is their purpose. So same goes, of course, for any reconfigurations, updating of routes, or any changes needed in routing. Finally, an important plus is what we already mentioned. Packets can usually take several different paths to reach the same destination. With static routing, you can add all the different paths and prioritize them manually, but things happen in real time. For example, one link is always going to be more congested than the other one, and it is impossible for you to manually adapt your routes to current situations. With routing protocols, however, that is completely doable. Not only do the protocol algorithms track the number of hops, they also are aware of congestion, different bandwidth capabilities of different links, etc. Anyways, that's it for the theory part. Let's go to our practical example in Cisco Packet Tracer. I've uploaded the file for you with this lesson. You can find it under resources. You need to have Cisco Packet Tracer installed on your computer, but that's fairly straightforward. I have a free course on how to do that on my Udemy channel, so go check that out if you find it too difficult to do on your own. Anyways, this example should show you a mixed configuration. All routers except router A have a routing protocol configured on them. So the idea of a routing table, which we are about to look into on router 1, is that each router should know exactly where each of these networks that I have labeled here on this simulation for you. So routers should know where to send a packet if that packet wants to go to any of these networks. All right, let's go to the enable configuration mode and type show IP route. That's the command that will display the entire routing table for us. You will see different entries here. S is for static route. R is for the route that was added by the routing protocol. In this case, I configured the routing protocol RIP. It's short for Routing Information Protocol. It's one of the older protocols out there, but it's super easy to configure, and that's why I chose that one. There's the C route, that's the directly connected route, and same goes for L. L is short for local here. So that would be all the labels we have in the routing table. And what is important for us is that when we move this out of the way a bit, we can see all of the networks that exist in our simulation in our routing table. Okay, let me really quickly show you the actual configuration of this router. We're going to focus on the part where routes were added. So you can see here router RIP configuration. This was summarized. This is a bit more complex IP addressing thing that we will not entirely cover in this course because it's really an in-depth thing. And then this is the static route that I added manually. Now, I'm going to try to explain to you in the simplest terms possible why I had to add this route here, because previously I mentioned that router A is the only one that doesn't have the routing protocol on, where I configure static routing. Well, what routing protocols do is they will exchange their entire routing information with each other. So for example, let's look at router C. Router C has 3 networks directly connected, or excuse me, 4 networks, 10.12, 10.13, 10.14, and 10.2. As you might have already noticed, we will use this second octet to distinguish between the different networks in this simulation. So router C has 4 networks directly connected to it, and when we use a routing protocol, we just need to basically switch on the routing protocol and share with the routing protocol which networks are directly connected to this router. That means that this router immediately knows, without any additional configuration, where to send packets that are destined to any of those 4 networks. In this case, 10.2, 10.12, 10.13, and 10.14. Router C will send that information to router B, for example. Because we set up the same routing protocol on router B, they will be able to communicate and understand each other. That's what protocols are for in the end, right? Well, router C will tell router B, I know how to reach these 4 networks. So, in case that somebody sends a packet to you and the packet wants to go to network 10.12, for example, send that packet over to me and I'll know what to do with it. And that's the whole purpose of routing at the end of the day. For the router, like from the perspective of the router just wants to get rid of the packet. It needs to figure out where to next forward that packet, and then it's just gone. It sends the packet out, and that's it for that router. It forgets about it. Now for router A, because I don't have that same routing protocol and I can't just communicate with these routers for them to tell me where exactly each network is, I had to into the router and type all of these networks out by hand. Obviously, the networks that are directly connected, I don't have to insert those into the routing table by hand, but I do have to manually configure all the other routes. Now, in the other direction, if this router A, had the routing protocol configured on it, it would inform all the other routers where this network 10.1.0.0 is located. But since we don't have the routing protocol configured there, this router is not going to send any information back to the other routers. So that's why I had to manually open every other router as well and tell each router where this network is located, or where to send a packet destined to that network shall that packet reach any of these routers, in this case router C. And that's actually the whole story. Let me just go to router A's routing table, show IP route, so that you can see that other than the few that are really directly connected, everything else is statically added. And yeah, Cisco will display it as directly connected as well. But if you look at these labels here, you'll notice that these are the static routes, or the manually configured routes. What's important for me is that the communication works. So I'm going to try to ping from PCX to PCY, and that's successful. Last but not least, let's go to simulation mode just to look at every step of that packet's path. The packet is created on PCX, the ping process is started, blah, 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 but we're interested what happens on the routers. If we go to router A, in the incoming part of the interface, we have on layer 3, the device looks up the destination IP address in the routing table, and then on the in the out part of the interface, in the outgoing part of the interface, the routing table finds a routing entry and then basically sends the packet forward. The next router is going to be router 1. Router 1 is going to go through the very same process. What is important for you actually to understand here is that the process is the same, regardless of how the route ended up in the routing table. So it's important that this information in the routing table is correct, and that is all. So whether we entered it manually or we entered it via the routing protocol, or the router found out about the route via the routing protocol, doesn't really matter. You're always going to get the same message, and we can confirm that on router C as well. Incoming, device looks up the destination IP address. Outgoing, the routing table finds a routing entry to the destination IP address. And then let's just see the package through. So it reaches a PCY, and since ping is an echo request, it goes back. And might be interesting to notice here that the packet goes back through a different path this time. I believe that's because I configured router C to send packets destined to 10.1 network through this interface here. So this was not the routing protocols doing. This was me configuring that route on router C manually. All right, our packet reached its destination, and that would be it for this lesson. Hope you found it useful. If you have any questions, please reach out in the Q&A section, and I'll be happy to reply. Bye. We have already discussed routing. We even mentioned some routing protocols. However, let's revisit that topic one more time and also get into more details. First, we need to understand what is an autonomous system. An autonomous system, in short AS, is a very large network or group of networks with a single routing policy. An example would be an internet service provider, a cloud provider, a large corporation, a university network, for instance. Actually, I have a picture for you, so let's look at that. The basic idea is that each box here is an autonomous system. Let's give them numbers. And you'll notice right away that they're different sizes made up of different devices and so on. What's important is that inside of these boxes, there is one type of routing protocols and outside another type. Let's talk about that now. So I just hinted that there's two types of routing protocols, and it has to do with inside and outside of autonomous systems. Let's talk about the inside, or as they are correctly called, interior gateway protocols. You'll also see them referenced by the acronym IGP, and as the name suggests, those are the protocols used inside an autonomous system. And it depends on how complex is the network, but it usually has a single routing policy. Now, what does that mean? Well, let's say that you work at an internet service provider, or for short, ISP, and that ISP has their own autonomous system. Next, let's imagine, as that is often the case, that this ISP has several teams working for it that are maintaining the network or everything inside the autonomous system. All of those engineers are likely to agree on a set of parameters which they will follow and or configure inside the network, such as IP addressing scheme, whitelists and blacklists, and finally routing. It's not going to work very well if everyone is allowed to make their own decisions and just, configure devices as they please. And in the case of routing protocols, the network is certainly not going to work, not well, but at all, if every engineer would just go ahead and configure any routing protocol they like best. So to conclude, what's meant by this single routing policy is that some network architect working inside the AS pointedly decides what routing protocols will be used, if some static routes are maybe needed, etc. Ideally, you'll have only one routing protocol inside the AS. However, it is possible to have multiple, but let's stick to one for now. And our option here in the last row are protocols RIP, short for Routing Information Protocol, OSPF, short for Open Shortest Path First. And I know that by the name, you'd think it probably just picks the shortest path in routing, but it's actually way more complex. Anyway, the third protocol is EIGRP, short for Enhanced Interior Gateway Routing Protocol. And this one is actually a proprietary one developed by Cisco, and it's only available on Cisco routers. And what are our options for EGP, External Gateway Protocols? Well, there's only one EGP currently in use, and that's BGP. Just to highlight the difference between interior and exterior routing protocols, you can choose the interior protocol, meaning as a network engineer or architect, which one you will use. But for exterior routing, that's actually internet routing, and you have only one option really, and that's a BGP. So what is BGP? Let's go back to our topology. If the interior routing protocols are limited to the insides of autonomous systems, then the exterior routing protocols happens here. We already said the only EGP in use today is BGP, short for Border Gateway Protocol, and that's the protocol used to route all of public internet's traffic. In essence, these routers that are the gateways exchange information about all the routes they know, and then those are propagated to everyone else. That is how every router participating in internet routing knows where all the other routes and networks are. All right, hope that was clear for you. That's it for this lesson. In this lesson, we make an introduction to the bottom two layers, link and physical. Let's get into it. Although the basic service of any link layer is to send a datagram from one device to another over a link, the details of the provided service can vary from one link layer protocol to the next. Possible services that can be offered by a link layer protocol include framing. Almost all link layer protocols encapsulate each network layer datagram within a link layer frame before transmission over the link. A frame consists of a data field in which the network layer datagram is inserted and several header fields. The structure of the frame, of course, is specified by the link layer protocol in use. Next, there's link access. There is a special protocol for this that specifies the rules by which a frame is transmitted onto the link. For example, the point-to-point links that have a single sender at one end of the link and a single receiver at the other end of the link. That protocol is simple or might not even be needed. The sender can send a frame whenever the link is idle. The more interesting case is when multiple nodes share a single broadcast link, the so-called multiple access problem. Here, the link access protocol serves to coordinate the frame transmissions of the many nodes. Now on to reliable delivery. When a link layer protocol provides reliable delivery service, it guarantees to move each network layer datagram across the link without error. Similar to a transport layer reliable delivery service, a link layer reliable delivery service can be achieved with acknowledgements and retransmissions. These tools are often used for links that are prone to high error rates, such as wireless, for example. One downside of this approach is that sometimes for the more reliable links, such as fiber, using these technologies might even be an overhead. But good news is that it is not mandatory to use them, which is why you will see some connection links run without acknowledgements and retransmissions on layer 2. Finally, and this is related to the previous point, obviously, in order to be able to provide reliable delivery, you need error detection and error correction capabilities. Such errors might happen due to signal attenuation, for example, or electromagnetic noise. Error detection is achieved by having the transmitting node include error detection bits in the frame and having the receiving node perform an error check. On layer 2, this is usually implemented in hardware, unlike on the network and transport layers. After all that, you might wonder, where are all those functionalities implemented? Well, for the most part, the link layer is implemented in a network adapter, also sometimes known as a network interface card, which NIC is short for. At the heart of the network adapter is the link layer controller. It's usually a single special purpose chip that implements many of the link layer services we mentioned a minute ago. Thus, much of a link layer controller's functionality is implemented in hardware. Therefore, if you as a network administrator need to control or reconfigure these functionalities, you'll depend on your hardware manufacturer to be able to do anything about it. An interesting fact to mention here is that until the late 1990s, most network adapters were physically separate cards, but increasingly network adapters are being integrated onto the host's motherboard, a so-called LAN-on motherboard configuration. And finally, let's talk about the physical layer, or layer 1 of the OSI model. A physical layer defines electrical and physical specification for devices. It defines the relationship between a device and a transmission medium, such as copper or optical cable. The major functions and services performed by the physical layer are listed here on our slide. Number 1, connection establishment. Obviously, a process responsible for establishing a link or a connection. Same goes for connection termination. Next, we have something called modulation, which in other words is conversion between the representation of digital data in user equipment and the corresponding signals transmitted over a communications channel. These are signals operating over the physical cabling, such as copper and optical fiber, or over a radio link. And finally, physical layer is responsible for participating in the process of sharing communication resources between multiple users. Activities taking place here are similar to flow control we mentioned on upper layers, including contention resolution. By the way, if you're not familiar with it, contention resolution here simply means avoiding collision between packets being transmitted at the same time or at a similar time. And that's enough on this topic. As always, shall you have any questions, feel free to ask in our Q&A section. Back when we discussed IP addresses, we mentioned that there's this other kind of addressing, physical. Here, we dive a bit deeper into that topic. Let's start from the definition. A MAC address, short of Media Access Control, and is also sometimes referred to as a hardware or physical address, is a unique 12-character alphanumeric attribute that is used to identify individual electronic devices on a network. Here's an example of what a MAC address looks like. And this is what you might also see out there. It's essentially the same number, but written in a different format. How do you find your own MAC address? If you're a Windows user, go to Command Prompt and type ipconfig/all. If you're a Linux or Mac user, just go with ifconfig, ifconfig instead of ipconfig. Obviously, I masked some of the details here as this info could be used in an attack. But anyway, further below in the output from the ipconfig command, you'll see your MAC address. There might be multiple MACs as your computer is likely to have several network adapters. For example, one for the physical interface, one for wireless, and then perhaps a VPN connection might have a separate one as well. All right, one more thing before we move on to the next topic. I want to stop for a second and explain why the MAC addresses look the way they do and what each part means. I made it sound like there's many parts just now, but there's not. There's only two. The OUY short for organizationally unique identifier, and the NIC specific part. They're each exactly half of those 6 bytes, meaning each part is 3 bytes. The first part is manufacturer specific, meaning every manufacturer that produces any type of device that requires a MAC address to function gets their own OUI, and as the name suggests, that is a unique identifier that uniquely identifies the device manufacturer. And then that manufacturer can use the second part however they wish. Of course, they'll want to save space and use those addresses intelligently. Although 3 bytes, or in bits, that's 24 bits, there's many combinations which allow many different addresses. But still, these devices are produced in the millions. All right, that's the basics on MAC addresses. In our next lesson, we'll talk how exactly they're used in computer networks. So see you there. Now that we've learned about MAC addresses, we can move on to another technology for moving packets around in a computer network, and that technology is called switching. As always, let's start from a definition. Simply put, switching is a process to forward packets coming in from one port to a port leading towards the destination. We have already talked about routing, and this sounds kind of familiar, right? Well, here's the difference. This is a simulation we'll use today, and it's almost the same as the one we've used so far. The only difference being the 2 new computers in network 10.1.0.0 on the left. Anyway, what we did before was send packets from computer X to computer Y. In order to do that successfully, we needed routing. Why? Well, because our packet traverses across different networks. However, if we send a packet to a device inside our own local network, for example, from computer X1 to computer X3, we'll be able to do that with only a switch. We don't really need a router. But wait a minute, we saw the router's routing tables and we learned how routers forward traffic by looking at destination IP addresses and finding them in the routing table. And a switch is a layer 2 device, which means it doesn't even support IP addresses. So how in the world does it know where to forward packets? Well, it uses MAC addresses. Let's see now how it works in the simulation. As always, you can find the simulation file in the resources section of this lesson. All right, so the new items in this simulation compared to before are these 2 PCs. We used to have only PCX, and now we have PCX2 and PCX3, and I renamed the PCX to X1 appropriately. Let's check what are the MAC addresses of these computers. Obviously, if these were real computers, you would need to open the computer, go to the desktop, find the MAC address. But since this is a simulation, we can just hover over this PC icon and look at MAC addresses on the far right of this message that just popped up. You can see here that this computer has 2 MAC addresses, one for the fast Ethernet interface and the other one for a Bluetooth interface. We are interested in the fast Ethernet MAC address. It's 0060. Let me try and label that. I'm just going to say 0060 for now. I'm going to press escape to get out of this thing here. And then let me look at other MAC addresses. If they are different enough, which looks like they are, I don't really need to write the whole MAC address here. I'm just going to take the first four numbers. So in this case, it's 0090 for x2. All right. And then for x3, it's 000C. Perfect. Now I'm going to open switch 1 and I'm going to check switch 1's MAC address table. To do that, you need to go into this enable configuration mode and type show MAC address table. Press enter and you will see that this table is empty. How come? Well, even if I didn't tell you this, you would probably be able to guess yourself after some thinking about it. How does a switch learn the MAC addresses? Well, these computers start sending packets. Let's send a packet from X1 to PCY as we did in our previous simulation. I'm going to repeat that. And now it's successful. Now I'm going to delete this ping. I don't really need it. This is just a simulation thing. Now again, I'm going to go to switch 1 and repeat the command by pressing the up arrow, show MAC address table. This time I have two MAC addresses in the table. 0060 is the X1 MAC address, and then there's this 00E0 MAC address, which I'll leave that to you to try to figure out. It's not that difficult. We want to focus on this local network here. All right, so switch 1 has learned that the 0060 MAC address is connected to the port Fast Ethernet 0/1. Let's hover over this interface here. It disappears really quickly, but you could see that that's the Fast Ethernet 0/1. So what does this tell you? The switch learns the MAC address as a packet comes in through that port. So the source MAC address of a packet that is sent by PCX1 is the MAC address of that PC. So the switch says, all right, someone with this MAC address is sending a packet on this port. That must mean that that device with this MAC address is located on that very port. So it remembers that in its MAC address table. Now let's say we want to send a packet to PC3. That packet goes through. Now I'm going to repeat this. Can you guess what happens now? Exactly. We learn a new MAC address, and this time it's the MAC address of PCX3. As we learned previously, the ping is an echo request, meaning that it's going to go from X1 to X3 and then X3 is going to return it. That's how switch 1 learned about X3's MAC address when it was returning the packet to X1. Let's look at the simulation. So X1 sends the packet goes up to switch 1 forwards the packet to X3 because it knows this. Okay, this time this is repeated now, but we'll get to it, don't worry. Switch 1 sends that packet to X3 and then it returns it back to X1 because switch 1 now knows where X1 is based on the MAC address table. So now it knows, but what it's going to do if we send the packet to X2? Obviously there is no 0090 here, so let's check again. Wait, something's changed. It hasn't. So what's going to happen when we send that packet? I'm going to delete this one and then let's go into the simulation first and try it out. Send a ping from X1 to X2. All right, this time we got two packets. It's not just the ping that we're sending out, it's the ARP packet as well. And we'll talk about ARP in our next lesson, so stay tuned. So what happens now is the ARP packets goes out and the switch sends what's called a broadcast. So it sends this package to everyone just to try to find how to reach the destination MAC address. The one that comes back is, the one that replies, the PC that actually replies, that's the one that recognized itself as the PC that has the destination MAC address. So it's going to reply. And in replying, the switch is going to say, okay, so this one replied, that's where this MAC address is. We repeat our command and voila, here it is, 0090. All right, we will clarify ARP a little more in the next lesson, so hopefully that will complete the picture here. See you in the next lesson. Bye-bye. In the previous lesson, we touched upon this protocol called ARP. Let's dive into details now. As always, we start from the definition. ARP, short for Address Resolution Protocol, is a Layer 2 protocol used to map MAC addresses to IP addresses. All hosts on a network are located by their IP address, but network interfaces do not have IP addresses. Physically, they have MAC addresses, or as we also call them, hardware addresses. ARP is the protocol used to associate the IP address to a MAC address. And we saw a little bit of how that happens in our simulation, but let's go through all the steps here. Long story short, let's say PCX1, we'll call it simply PC1 here. Let's say PC1 is sending something to PC2. First, PC1 will check its local cache, or in other words, its ARP table. If there's no entry for PC2 there, PC1 will send out an ARP request. The ARP request is a broadcast by definition, meaning it will go to all network devices on that network segment. To clarify, this packet will reach every device connected to the same switch as PC1. Once PC1's ARP request reaches PC2, before replying, PC2 will first memorize PC1's IP and MAC address mapping, since obviously PC1 is trying to talk to PC2. That tells PC2 it will soon need PC1's information. Next, PC2 replies via ARP protocol, and then once that response reaches PC1, it will memorize the MAC and IP mapping as well. Now, that example was for when PC1 and PC2 are in the same network segment. What if PC2 was in a remote network, meaning there's a router between PC1 and PC2? Let's use our simulation network, and this time imagine we are trying to connect PCX1 and PCY or PCY. Intuitively, you might think that X1 will simply send an ARP request all the way to Y, but that's not what actually happens. This is how it goes. X1 will send an ARP request for its gateway IP. In this case, X1's gateway is router A. Router A will, following the routing table instructions, look for the next hop's IP address or MAC address of that IP address, which let's say is router 1. Router 1 will go to router C, and finally router C will send an ARP request for PCY's MAC to find the IP and MAC address mapping. And that's pretty much what ARP is all about. Hope it was clear enough for you. If you have any questions, as always, I'm happy to help you. Just post it in the Q&A or send me a direct message. Bye. In this lesson, we explore the security aspect of ARP. As a matter of fact, many of the network protocols we discussed in this course have similar security flaws as you'll see in ARP, but this one is the easiest to understand, especially for those just starting to learn about computer networks. So, what is the issue with ARP? Well, one characteristic of ARP that I didn't mention yet, and it is fully legal and even designed that way in ARP's RFC, short for Request for Comment document, is that clients are totally allowed and expected to send unsolicited ARP replies. What exactly does that mean? You remember that in order for a network device to learn another device's MAC address, it will send out an ARP request saying something like, hey, who has this IP? And then it will list the IP in hopes that the request will reach that very device and it will reply with its MAC address. Now, if you're a malicious actor and not a legitimate, well-meaning user of the network, you'll see instantly how that's a problem. For those of us who don't think like a hacker 24/7, let me explain with an example. Let's look at this picture here. Notice that there's device A, the router, device B, the laptop, and device C, someone who looks like a ninja running around with some stick. Joking aside, let's dive into this example. So the hacker is MAC C, IP address 3. Router is MAC A, IP address 1. And the laptop is MAC B, IP address 2. The hacker sends both of them an ARP reply with information that IP2 and IP1 belong to the device with MAC address C. MAC address C, again, belongs to the hacker sending these false messages. In essence, he's telling them that he is configured with those IP addresses. And that will result in the following. Both of those devices that were just fed wrong information, the router and the laptop, will send their traffic to the attacker with MAC address C, even when they want to send traffic to the other device. How? Well, remember that switches use MAC addresses and not IP addresses. That's right. If the laptop wants to send a message to the router, it will use destination IP address 10.1.1.1, but in its ARP table, it will find a wrongful mapping of 10.1.1.1 with MAC C, and as long as it uses that MAC address, the packet will end up being sent to the attacker. Of course, the attacker can use the same approach in removing evidence by simply sending out correct information right after the damage was done, meaning right after he or she has scooped all the wanted information. Oh, and if you're wondering what might solve this issue, don't worry, there's configurations available to help with it. One of those is DAI, short for Dynamic ARP Inspection. It's a feature that can be configured on network devices to detect this behavior and also set up some sort of remediation, such as blocking that port where the hacker is suspected to have connected to, for example. All right, this was short but sweet. My goal was to make you aware of some of the security issues which come in hand with these protocols. Hope it was clear and you found it useful. It's time to learn about VLANs, which stands for Virtual Local Area Networks. Officially, a VLAN is a logical subnetwork that groups a collection of devices from different physical LANs. Let's look at an example and you'll immediately understand what I'm talking about. What we have here are two identical networks. Actually, what I did here is I set up this one on the left and then I copied it, and then when I pasted it, as you can see, it's the same names, it only has this one in the brackets which tells you it's a copy. But the difference is that this is a plain switched network. As you can see, there are no routers here. However, there are no VLANs configured in this network on the left. There are VLANs configured on this network on the right, and those are VLAN 10 and VLAN 20. If you have trouble seeing the difference between these two colors, I'm going to list which computers belong to which VLAN right now. So VLAN 10 is the green VLAN, and PCs 1, 3, 5, and 6 belong to VLAN 10, the green VLAN, and then VLAN 20 is red, and PCs 2, 4, 7, and 8 belong to that VLAN, VLAN 20. Speaking of VLANs I configured manually, this might be the right time to let you know that this entire time, in every simulation we had until now, we already had one VLAN configured, and that is the default VLAN, VLAN 1. So in this network right here, or on any switch, if you hovered over the switch, let me actually add a new one so that you don't think I might have configured something here. If you hover over, hold on, you will see in the third column under VLAN that all the ports belong to VLAN 1. I'm going to remove this switch real quick. And let's continue with our example. Other than the VLANs, I want to also point out that all of these computers belong in the same subnet. So if you hover over all of the PCs, you will see that each PC has an IP address starting with 10.0.0, and then only the fourth octet is different. So PC1 is 10.0.0.1, PC2 is 10.0.0.2, PC3 is 10.0.0.3, etc. If you do the same thing for the network on the right, you will see that they have the same IP addresses. However, these two are not connected. They could be entirely different simulations. I just configured it this way so that it's easier visually for you to compare the two networks. So let's go ahead and test these out. I'm going to send a simple ping in between the PCs. Again, these two networks are completely separated. Computers in the two networks cannot communicate. So the purpose of this simulation is to look at the difference in behavior of the network when there are VLANs configured and when there are no VLANs configured. So on the network, in the network on the left side, there is no VLANs. There's just VLAN 1, but that's as if there's no VLANs at all. We're going to try to ping from PC1 to PC4, for example, and that's successful, and then from PC2 to PC7, for example, and that's successful. So these pings travel between these computers without any issues. There's no VLANs between them, nothing like that. Let's delete the pings and focus on the network on the right. Here, I'm going to first start pinging in between the computers that belong to the same VLANs, because that's the purpose of VLANs. We want to create virtual LANs in a pool of devices that belong in the same physical LAN. So let me try pinging from PC1 to PC5, for example. That's successful. That should be that way. PC3 to PC6, PC5 to PC6, that's all working as expected. Let's test VLAN 20. On switch 5, we have two computers that belong in the same VLAN connected to the same switch. That's very fast and successful. All right, let's now try to ping between the computers that belong in different VLANs and see what happens. PC1 to PC2, they're connected to the same switch and they belong in the same subnet IP address wise, but there's no communication between them. Let's try that again. Failed again. Once more, failed one more time. Let's go to the simulation to see exactly what's going on here. We can see two packets being created here. One is ICMP, which is the ping we are trying to send out, and the other one is ARP. So the way VLANs work is devices belonging in the same VLAN will have all possible traffic allowed in between them, but the devices belonging in different VLANs will have all possible traffic forbidden between them, including protocols such as ARP, DHCP, DNS, etc. So those are not going to work as well. And ARP is a broadcast packet. So let's see what happens here. I'm going to click forward. The ARP packet reaches switch 3 here, where PC2 is connected. So just for a reminder, we tried the ping between PC1 and PC2. They're connected to the same switch. And then this switch, because the ARP request is a broadcast type of a packet, is going to send out those packets everywhere, but only on the links that can carry this VLAN from where the packet is coming. So for this PC1, only the devices that belong to the same VLAN are visible, including also these links between the switches, obviously, because those links have to carry several different VLANs. And we have one more slide to go through after this simulation. You will see that these links are called trunks, and they can carry multiple different VLANs. But these links over here that connect the endpoint devices, or in this case computers, to the switch are not trunks. They cannot carry several different VLANs. They can only carry one VLAN that is configured on the port of the switch. And yeah, if we continue the simulation, you will see these packets continue to search for the ARP answer, but they will never find it because this computer was trying to reach a device that does not belong in the same VLAN as the sending computer does. I'm going to stop the simulation right here, delete this ping request, and let's go back to our slide. One thing to point out here, as you could see in our simulation, are some of the reasons or some of the top reasons why you would want to implement VLANs. First, you saw the example with ARP. ARP is one of the protocols that sends broadcast packets. So by implementing VLANs, you are limiting the broadcast area, which declutters the network actually. And then also security, because this way you are limiting who can communicate with whom. All right, I want to mention several other important facts related to VLANs. First, we mentioned VLAN IDs, so you might wonder what's an appropriate VLAN ID to assign. We used 10 and 20 in our example, but valid IDs are from 1, which is the default, to 4049. Originally, the normal range was from 1 to 1001, and then it was extended due to growth of LAN networks, basically. Second, communication between different VLANs can be established again, and this is done with the use of routers and routing. Next, the link that carries different VLANs, or in other words, links between switches that we saw in our examples, that can transport multiple VLANs are called trunk links. Likewise, those links that can only transfer packets belonging to one VLAN are called access links, and those are the links between switches and endpoints usually. And that's your basics in VLANs. I hope it improved your understanding of this topic, but if not, please ask your question in the Q&A section or send me a direct message. When we learned about the OSI model, I mentioned Ethernet as one of the protocols on the link layer. And perhaps you got a bit of an idea about what it is based on our packet tracer simulations, where most of the interfaces were either fast Ethernet or gigabit Ethernet. But the Ethernet protocol is a bit more than just interfaces. As always, let's define it first. Ethernet is a communication protocol which connects devices on a network over a wired connection. And as any other protocol we've mentioned so far, Ethernet also has its own standard for frames transferred over Ethernet links. First, there's the 7-byte preamble and 1-byte SFD, or start of frame delimiter. In short, preamble is a pattern of alternative ones and zeros, which indicates starting of the frame and allows sender and receiver to establish bit synchronization. Initially, preamble was introduced to allow for the loss of a few bits due to signal delays, and then SFD indicates the beginning of the frame. And now the important part, destination and source addresses, are the MAC addresses we already learned about. And then length obviously specifies the length of the entire Ethernet frame. Data field is where actual data can be added, and it is also called payload. Here, both the data and IP header will be inserted if IP is used over Ethernet. Finally, CRC field carries the frame's hash value, which is calculated at the receiver's end too, and then it's compared to the value from this frame. If there's a mismatch, that tells us that the packet has been modified or some parts of it were lost on its way from source to destination. Lastly, I want to introduce these Ethernet standards to you. This isn't something you're expected to know by heart, but you're likely to encounter these terms in the computer networking literature and in the real world too. So basically, this is just the terminology for different Ethernet standards, and it's used to express which transmission type, speed, cabling type, or length is appropriate for each of the listed standards. We'll go together through a few of these. First one up is the 10-base-5 standard in IEEE world. That's the IEEE 802.3 protocol, or you could also call it a standard. It's just the IEEE code, if you will. Also, this particular one is sometimes referred to as TIC-net because it uses TIC coaxial cable, but the most important parameters are the speed, which is 10 megabits per second, and that you can use a coaxial cable for up to 500 meters to connect the devices. Also, the cable types you can see in the column minimum cable grade can help you choose a cable to buy if you need to connect such two devices. All right, let's not go through all of them. It's clear what this table displays. I'd just point out two standards you're most likely to see in the real world out there. 100 base T/TX and the 1000 base T. These are the 100 megabits per second and 1 gigabit per second UTP cables of 5th and 6th category. If you have any cabling in your home or at work, I suggest you trace that cable and check any words you can find on it. Then check back to this lesson and see if you can find it here. And we're going to finish our lesson with that nice little homework for you. Bye! You are surely aware of the increase in wireless devices in networks today. That's why we can't finish this course without at least scratching the surface of mobility and wireless connectivity. Let's first identify some basic elements we must be familiar with in order to discuss wireless networks. First, the reason why we are building a wireless network is there are wireless hosts in need of connecting. A wireless host might be a laptop, a smartphone, or a desktop computer. Second, there's wireless links. Different wireless link technologies have different transmission rates and can transmit over different distances. Two key characteristics you should know about are coverage area and link rate, which are fortunately both self-explanatory. Next, base stations. They are key parts of the wireless network infrastructure. In essence, a base station is responsible for sending and receiving data to and from wireless hosts associated with that base station. By the way, when we say a wireless host is associated with a base station, we mean that one, the host is within the wireless communication distance of that base station, and two, that the host uses that base station to relay data between the host and the larger network. Examples of base stations are, by the way, both cell towers, but also access points in wireless LANs. And just to add here, there's another less important, but however interesting term, handoff. And that is a process that takes place when a mobile host moves beyond the range of one base station and into the range of another one. This is when it will change its point of attachment. In essence, that's what a handoff is. Finally, the term network infrastructure in this context refers to the larger network with which a wireless host will want to communicate. Another topic I'd like to cover with you, which is not necessary to know, but if you decide to study wireless technologies a bit deeper, this will be super useful to you. There's a few most important differences, or you could say challenges, in wireless links compared to wired links. Let's quickly understand each one. Decreasing signal strength. See, electromagnetic radiation fades as it passes through objects or around objects. For example, a radio signal passing through a wall. Even in free space, the signal will disperse, resulting in decreased signal strength. By the way, this is sometimes referred to as path loss. In plain English, the signal will simply decrease as the distance between sender and receiver increases. Next issue is interference from other sources. What does that mean? Well, radio sources transmitting in the same frequency will interfere with each other. For example, 2.4 gigahertz wireless phones and Wi-Fi LANs transmit in the same frequency band. Thus, the wireless LAN user talking on a 2.4 gigahertz wireless phone can expect that neither the network nor the phone will perform particularly well. In addition to interference from transmitting sources, electromagnetic noise within the environment, for example, in a nearby motor or a microwave, will also cause trouble. Third, there's something called multipath propagation. This occurs when portions of the electromagnetic wave reflect off objects and also the ground, which results in the signal taking paths of different lengths between a sender and receiver. This results in the blurring of the received signal. Finally, the SNR, short for signal-to-noise ratio. Simply put, SNR is a relative measure of the strength of the received signal. To simplify it for you, there's two words in this term: signal and noise. Signal would be the original information that was transmitted, a verbatim copy, so to say. Noise are all the modifications to that signal introduced by some or all of the issues we just now listed: decreased signal strength, interference from other sources, or multipath propagation. By the way, SNR is typically measured in units of decibels, just so you know if you see it somewhere, that's what it is. Of course, for each of these topics, there's an entire science behind it, but for the basics, this is more than you need to know to understand fundamentally how wireless networks operate and what are the major challenges there. All right, we have 2 more lectures dealing with this topic, so see you there. And finally, it's time to talk about Wi-Fi. It's everywhere around us, so we already know its practical use. However, in this lesson, we'll get into a bit more details on the technical side of it. Let's go. First, an interesting story about the name of Wi-Fi. There is a non-profit organization actually called Wi-Fi Alliance, and they own the Wi-Fi trademark that you can see here on the slide. The name Wi-Fi was coined by a brand consulting firm called Interbrand. The Wi-Fi Alliance had hired Interbrand to create a name that was a little catchier than IEEE 802.11b direct sequence, which is the IEEE standard we'll talk about in a moment. Now, formally, Wi-Fi, technically speaking, is a family of wireless networking protocols based on IEEE 802.11 family of standards, which are commonly used for mostly access to networks and the internet. Now, this table shows all the Wi-Fi standards that existed over the years. First, there was the original 802.11, which is not showed in this table as it was deprecated. And the 802.11a is actually pretty similar. They both were developed to work on the 5 gigahertz band with maximum data rate of 54 megabits per second. However, the 5 gigahertz frequency has more difficulty with objects in the signal's path, so the range is quite poor. That is, back then this was difficult to solve, so the next standard, IEEE 802.11b, was the one to kickstart Wi-Fi's popularity as a technology. Now, let me skip a few rows to IEEE 802.11ac, which is what's most widespread today. It was developed in 2014, and as you'll notice, we're back to using 5 gigahertz. However, this time it's way more stable. Plus, the data range is also much, much higher at 1.3 gigabits per second. Last but not least, the newest one, IEEE 802.11ax, also called Wi-Fi 6, was developed in 2019, and the device manufacturers as well as the users are still adapting to that one. I say that because you might think, well, why doesn't everyone use the newest standard with its obvious benefit of the higher speeds? And the answer to that is simple. Let's say we're looking at your phone. If you change yours every year or so, it likely supports both these frequency rates and the data rates. However, not all people do that, nor need that kind of speeds. Therefore, it takes time for the technology to become accepted and mass used. Anyway, the last one, 802.11be, if you look at the year, you'll realize it's a thing of the future, expected to come out sometime around year 2025. So stay tuned for that. Similarly to our introductory lesson, let's break out the Wi-Fi technology by its basic elements. First, there's something called a BSS, short for Basic Service Set. It's the fundamental building block of the 802.11 architecture, and it contains one or more wireless stations and a central base station known as an access point, or in short, AP. In one of our packet tracer simulation, we had this topology, and in that scenario, this is an example of a BSS. There's an access point in there, and there's a wireless station there too. Okay, let's move on. Next, we have SSIDs, and you're probably already aware of those. It's short for Service Set Identifier, and it's simply a name for our basic service set we just described. In plain English, it's the name of your Wi-Fi network. And finally, we reach this interesting term, Wi-Fi jungle. A Wi-Fi jungle is any physical location where a wireless station receives a sufficiently strong signal from two or more access points. For example, in crowded areas such as cafes in densely populated cities, a wireless station can pick up a signal from numerous nearby access points. One of the access points might be managed by that cafe we just mentioned, while the other access points might be in residential apartments nearby. Now, suppose you enter such a Wi-Fi jungle with your portable computer, seeking wireless internet access and, a coffee. Suppose there are 5 access points in the Wi-Fi jungle. To gain internet access, your wireless station, aka laptop, needs to join exactly one of these subnets and hence needs to associate with exactly one of the access points. Associating means the wireless station creates a virtual wire between itself and the access point. Specifically, only the associated access point will send data to your wireless station, and your wireless station or your laptop will send data frames into the internet only through the associated access point. But how does your wireless station associate with a particular AP? And more fundamentally, how does your wireless station know which APs, if any, are out there in the jungle? Well, the 802.11 standard requires that an AP periodically sends beacon frames, each of which includes that access point's SSID and MAC address. Your wireless station, knowing that APs are sending out beacon frames, scans the channels, seeking beacon frames from any APs that may be out there. Having learned about available APs from the beacon frames, you or your wireless host select one of the APs for association. The process of scanning channels and listening for beacon frames is known as passive scanning. A wireless host can also perform active scanning by broadcasting a probe frame that will be received by all APs within your laptop's range. Access points then respond to your probe request frame with a probe response frame. The wireless host can then choose the AP with which to associate from among the responding APs. And that, my friends, is the story of Wi-Fi. Hope you learned something new, and I'll see you in the next lesson. And now a bit of cellular. That's our topic for this lesson, so let's get into it. First and foremost, GSM. What is GSM? Why we need to discuss it here? Let's see. GSM, short for Global System for Mobile Communications. Hold on, pause right there. Actually, GSM acronym was originally derived from Groupe Spécial Mobile, but was then changed later on. Americans, you know. Just kidding. Anyways, GSM is a standard developed by the European Telecommunications Standards Institute to describe the protocols for second generation, or otherwise known as 2G, digital cellular networks used by mobile devices such as mobile phones and tablets. Basically, GSM digitizes and compresses data and then sends it down a communication channel. Then, over time, the technology expanded to transferring data via packets, which is how we got GPRS, short for General Packet Radio Service. And what will help you remember this best is the fact that GPRS is usually charged from customers according to the total volume of data transferred during a month. Typically, unlike the previous system, which was called circuit switching and was billed per minute or per connection time rather than how much of the data was actually used up or transferred. But just to clarify, GPRS is a part of the GSM. It's not like a next generation GSM. Let me give you some of the examples of new services that were brought by GPRS. You probably forgot some of those or didn't even use them, but let me tell you, mobile providers marketed those options like it was rocket science back then. First, SMS messaging and broadcasting. SMS was there with GSM too, but GPRS allowed for higher speeds. Yep, that was a thing, faster SMS. And for broadcasting, it's still used for marketing, for example. You just need to think about the promotional texts you still get to this day. That's what SMS broadcasting is for. Next, there's the always-on internet access. Simply put, this describes the mode where you are always connected to the internet and you are not charged for the time spent online, but rather the amount of data transferred. MMS, if you remember, before MMS, there was no way to send any type of multimedia, a picture, a sound, etc. There was no messaging apps back then. So that is what MMS was used for. And by the way, I worked at a telecommunications company recently enough to be able to tell you that people still use MMS. Moving on to POC, this is practically just voice calls, but transferred in packets, kind of like the voice over IP. As a user, you don't really need to know the difference. Your job is to simply have a phone call. And the last two, internet apps for smartphones and point-to-point internetworking, these are the well-known apps we still use today. All right, now that we've established what GSM and GPRS are, let's talk the generations. G1 or Generation 1 was designed exclusively for just phone calls And hey, it was a big deal back then. We went from being physically tied to a landline phone to a cell phone. It was a big leap. Next came 2G, and we already named the two biggest improvements, which have to do with texting and multimedia messages. With 3G, the term mobile broadband was introduced, as this is the first time cellular networks could handle a high enough bandwidth to transfer, for example, video calls. And if you remember, this was also heavily advertised by service providers, and cell phone manufacturers scrambled to add front cameras to their phones. And finally, the 4G, which simply put just supports higher speeds than 3G. So all of these services we mentioned previously are still there, but as the speeds increased, so did the quality of the apps, games, video calls, and everything that comes with it. And then 5G isn't here because it's also pretty much just enables higher speeds. That does introduce some new possibilities, just like each of the Gs did so far, but the basic cellular logic is very comparable. So we skip the controversial 5G. And finally, I want to tell you a little bit about the typical cellular architecture. This picture here comes from the Karos-Ross book on computer networking, which if you are studying this topic for a university exam, for example, I can highly recommend. However, as a network admin working with networks as a day-to-day job, that book is not very practical. Anyways, this picture nicely depicts what I want to emphasize right now, which is mobility and cells. Here we can see that each cell contains something called a BTS, short for base transceiver station. That's this tower you can see in the center of each cell. And what this station does is it transmits to and receives signals from the mobile devices, or as they are called here, mobile subscribers. You see one mobile device in a car and two other ones as well. Anyway, the other two important devices we see here are the BSC, short for base station controller, and the MSC, mobile switching center. BSC is responsible for allocation of the transceiver station's radio channels. Again, that's the telco tower in the middle of each cell. So BSC is actually the brain behind which radio channel is allocated to which mobile subscriber. BSC is also the one to find where a cell phone is located in which cell and perform handoff. Handoff is why this car is pictured here, and we've already mentioned this in the introductory lesson, but again, handoff happens when a mobile user or subscriber moves from one cell to another. Of course, since each transceiver only covers their own cell, this is the subscriber now must establish a connection, or as this is called in the literature, the subscriber associates with another base station. That's handoff. Okay, back to the devices in the picture now. There's two devices left, MSC and MSC gateway. MSC, short for Mobile Switching Center, is responsible for user authorization, or in other words, if the user is at all allowed to connect to the network. Also, MSC will handle call establishment, call handoff, and call termination. MSC Gateway, the next device up the line, stands between one provider's network and the other provider's networks, including the landline phone system and everything else that's out there. And that, my friends, is all we will cover on this topic of cellular networks. There's certainly more to this, all the radio stuff, the signals, the radio networks controllers, and so on and so on. But radio and signals are an entire different discipline that you don't really need in this computer networks fundamentals scenario. It's useful to be informed, which after taking these lessons, you are. That's it for now. Bye. This will be our final chapter, and I want to start it off by explaining what is hacking, why the hackers hack, because oftentimes the motivation behind attacks is important to detecting and or stopping attacks before they create damage. So what is hacking? Per definition, hacking is an act that seeks to compromise digital devices such as computers, smartphones, or even entire networks. Next logical question would be, why? Well, there's many motivators behind it, but some of the most prominent ones would be data theft, whether it be for financial gain. For example, lots of stolen data is offered for sale on the dark web. It could be for personal vendetta. It could be to damage a brand's reputation, gaining access. While it could be inspired by any of the other 3 points here, it could also be done for curiosity, personal interests, or, spying. Next, there's reputation damage. This occurs especially when there's competition. Let's say that there is a mobile operator and they have one competitor. It could be some very small country like an island, for example. And the country is small enough that 2 mobile providers is enough. People will choose the reliable one or the one that they trust more. If one attacks the other, leaks damaging information, or hits them with a DDoS attack, disabling their internet service, that is instant gain for the competitor. Fourth example of hackers' goals is activism. Hackers motivated by activism are often called hacktivists. They will target websites or IT infrastructure of institutions, organizations, or governments they disagree with. And now that we have established the basics, let's get into some of the most popular cyber attacks out there today in our next lesson. In this lesson, we focus on the top 5 common cyber threats or attacks out in the wild right now. Here they are. First off, phishing. It's actually the #1 issue in security. And basically, it's a type of social engineering where an attacker sends a fraudulent message designed to trick a person into revealing sensitive information to the attacker, or to deploy a malicious software on the victim's infrastructure, like ransomware, for example. Here is a short clip on what that looks like from my other course, Information Security Fundamentals.
Let's say that an employee receives an engaging email with a link to follow up. For example, it might be a message from PayPal saying that a transaction has been rejected. If the user initiated some transaction recently, they might want to know what happened with it. And if they didn't, they might think that PayPal stopped a suspicious transaction from happening and will want to see the details. Let's say the email was sent from support@paypal.com instead of support@paypal.com or something similar. The user might easily not pay attention to this difference in one letter and click on a link provided in the body of the message. The landing web page looks exactly like PayPal's landing page, and this is easy for an attacker to achieve. There's actually tools on the dark web that allow you to copy an entire website. Let's say that our target employee then enters their credentials, but instead going to PayPal, they end up going to the attacker who set up the fake website. This is one of the ways hackers generally steal credentials. The attacker might even forward those credentials to the real website and redirect the user there, which is when the real PayPal sends them a second factor of authentication, an email or a text message. To clarify, our target enters their email and password, and since this is a malicious copy of the website, those email and password details go to attacker, who can then use them to log in themselves and pay with this person's PayPal. But then the attacker might also write a script that will open the actual PayPal website, input the credentials from the unsuspecting victim into the real website, and then show the target the actual PayPal page. The target will then access their real account. They will see that there was no transaction rejected and probably think no more of it, assuming that it was a mistake. Of course, we only used PayPal here for the sake of this example, but in reality, attackers will often investigate which tools an organization uses if they are targeting employees of a specific company. They will investigate what does that company use, for example, Microsoft Office tools or communication tools that employees would expect to get emails from, and also for which AD accounts are used. So these Microsoft tools usually have the single sign-on capability, and you can log into them with your AD account. And an attacker getting their hands on AD credentials that belong to an organization is simply invaluable.
Next, there's viruses/malware. Malware, by the way, is short for malicious software and is usually a file or a code. It's typically delivered over network, and its primary purpose is to infect, explore, steal, or virtually conduct any other behavior the attacker wants. This is why they're so dangerous. It could be any code that, by infecting a target host, gains enough privilege to run. Anyways, there's a few terms related to malware like viruses, worms, Trojan horses. In short, the difference is that viruses connect to another legitimate software inside the computer, and the main goal is to harm the computer system. Worms, on the other hand, will replicate itself, and the main consequence of this is slowing down a computer system. And finally, the Trojan horse attack. The goal there is to capture information about computer systems, computer networks, or other IT assets. There's a few more terms than that, but these are the top three. Moving on to our next threat, ransomware. It's basically a malware which typically encrypts important information, and then the attackers demand ransom from the victim. Now, the victim, depending on how important the files are, will or will not pay the ransom. For example, in case of hospitals, this data is often even time critical. So the engineers tasked with trying to recover data are under enormous time pressure to do so quickly. If there is no way to decrypt the data, their best option often is to simply pay the ransom. I mean, I say it simply, but sometimes the attackers asks for millions of dollars, so it's difficult to decide. It's a bad situation, however you look at it. Okay, next we got DDoS. Now, this is a true network attack. Per definition, DOS, short for denial of service, is a resource consumption attack that has the primary goal of preventing legitimate activity on a victimized system. A DOS attack renders the target unable to respond to legitimate traffic. And then D in DDoS is a distributed DOS attack, which means many attackers target one victim. This is usually achieved using botnets. Again, these can be achieved by overwhelming a server with requests or completely saturating a link with any type of traffic, really. All that is important for the attacker to do is just send more data than the link or the router or a switch can handle at a given time. Some countermeasures against DDoS attacks are firewalls, special router configurations, and we will discuss firewalls in our next lesson. Lastly, there's the input validation attacks, and one big such attack is the SQL injection attack, where the attacker uses a misconfigured input form, such as a text box on a website, to, instead of inserting expected data, such as a username or some other information, they will insert an SQL command and reach all the way to the database and exfiltrate information out of that database. The database could, for example, be holding usernames and passwords. Of course, developers can avoid this vulnerability by performing input validation, which in essence means there is some process in the background checking that data that was typed in makes sense. For example, if you're asked to enter a name, you can't enter numbers. Or, when you need to enter your email somewhere and it will not let you submit if there's not an @ or a dot in there, which tells the website you did not enter a correct email address. Other than these well-known threats that a simple Google search will also return, there is this list, which is very well known in the security circles. It's called OWASP Top 10. Let me explain first what OWASP is. First of all, it's short for Open Web Application Security Project, and their top 10 list will tell you what are the most critical security risks to web applications for the previous year, though. This will be interesting to you if you're an application developer, an application security engineer or specialist, or if you hold any type of security job. You're likely to need this information because you should at least be aware of the current threats existing out there that you might eventually need to defend your organization against. That's it for now. See you in the next lesson. As promised, on to the topic of firewalls. Firewalls are devices through which network traffic flows, and depending on the configuration, firewalls can inspect that traffic, collect data for statistics and forensics, allow or block the traffic. In essence, the job of a firewall is to block unsolicited incoming traffic from the internet towards the intranet. Or, as is labeled here in this picture, WAN is the public internet and LAN is our local trusted network. There is more ways to look at separation between inside and outside. And one other way that's common in security is in regards of trust. When firewalls are configured to make a distinction between the two or more networks they're connecting, those networks are also called zones and are separated as trusted and untrusted zones. In our picture here, the untrusted zone would be the WAN side, and the trusted one would be the LAN side of the firewall. Let's now look at network architecture and where the firewalls are placed within it. Truth is, firewalls can replace routers altogether, depending on the needs of the organization. In such a setup, that firewall would be called a perimeter firewall. Let's look at our new architecture here. We have several different networks all connecting to those two central devices with bricks and little fires in the corners. As we already established, those are firewalls. The other networks connect via different devices to the firewalls and also go out to the internet through those firewalls. And then there's this VPN connected smaller network in the upper left corner. Something that's important to understand here is that firewalls mustn't always be physically put on the border itself. They are also placed inside networks, usually with the goal to provide visibility and protection from internal threats. Depending on the needs of the organization, again, there are specialized firewalls such as a core and data center firewalls, for example. Core firewalls, or packet core firewall, as they're also called, are used by telecoms as they are designed to address security use cases in mobile and IoT networks, which in plain language means that they support inspection of specific telco protocols called signaling protocols. Next, a data center firewall is again a specialized firewall placed, as its name implies, inside a data center network. Another type of firewall that frankly doesn't have the best reputation among network engineers is a WAF, which is short for Web Application Firewall. And there's an alternate name I saw on Twitter a few years ago, which is a very annoying firewall. And yes, there is a grammatical mistake in there, I know. However, it tells you that these firewalls can cause trouble if they're not configured correctly. Let's see what they're all about. Oh, and by the way, in this picture here, the Web Application Firewall is the device with a red globe symbol on a brick wall rectangle. As for physical placement of a WAF inside an enterprise network, there are several possibilities for implementation. However, the only important thing is that the WAF is placed between the internet as a source of potential threats and the web server that is being protected. So finally, what WAFs do is they help protect specifically web applications by filtering and monitoring HTTP and HTTPS traffic between a web application or web server and the internet. It operates on the highest OSI layer, the application layer, and it's specifically designed to analyze each HTTP and HTTPS request directed at a web application. WAFs come in the form of an appliance, server plugin, or a filter, and may be customized to an application. However, it is important to note that in case an application adapted policy is applied, the policy must be well maintained, which means that every time the web app is modified, the policy needs to be adjusted as well. In conclusion, the main job of firewalls is to filter traffic, meaning block any suspicious or unwanted traffic that wants to come into our network based on either manually set up rules, for example, block this specific source, or geolocation, for example, or don't allow upload of large amounts of data outside of business hours, and so on. And another way to use a firewall would be with automatized features such as machine learning, which at this point every manufacturer claims their devices do. In essence, what that means is that the firewall will learn through time how the normal behavior looks like, and then block any anomalies that pop up compared to that learned normal behavior. And that's that for this lesson. See you in the next one. Another network security solution that is really helpful to have in a network is intrusion detection and/or prevention. Let's dive into the details. The main difference between the two is what you can already see from the title. Intrusion detection system can't prevent attacks, and intrusion prevention can both detect and prevent. Here's a visual to help us in understanding. On the left side, there's a network that uses an IDS, intrusion detection. That IDS is located somewhere in the network. On the right-hand side, we have an environment that has an IPS installed. The IPS must be in line, or in other words, in the way of the traffic, meaning it must be strategically placed on the link through which all traffic we want to inspect and protect passes. Let me go back to the IDS for a second to compare again. So we just established that an IPS is able to both detect and prevent malicious traffic from entering our network by scanning all the traffic that passes through and discarding those packets it deems malicious or as part of some attack against the resources inside the network. IDS, on the other hand, it only collects copies of the packets that go through the network. And if you look closer, the IDS on the picture here is connected to a switch. What that switch does is it mirrors, which in plain English means that it copies all the packets that go through it and forwards those copies to the port where the IDS sensor is attached. The IDS then processes all the packets, and if it's configured to store everything, it will, but that is not its primary function actually. Its primary function is to compare the behavior of the traffic that's passing by to signatures and rules the IDS engines have. Those signatures or rules are simply descriptions of malicious behavior. For example, no legitimate software application or user is going to test 200 different ports in a time range of 1 minute, for example. That behavior obviously points to a port scan, which are usually a step before an attempted intrusion if some open ports are found. If you are someday tasked with deciding which one of these should be used in a network you're responsible for, be aware of this one important factor. IPSs, in order to block malicious traffic, must either be implemented inline or as host-based IPSs, meaning installing an agent on a computer or server or database. With inline implementation, you'll have to invest in a really powerful IPS, as your speed rates will depend on how quickly that IPS can process all the packets and forward them further down the link. As for installing agents on endpoints, there is a risk of overwhelming those hosts, be it a laptop or a server. These cons are the main reasons experts choose IDSs. Yes, you can only become aware of the threat once it actually happens, but you'll usually be able to catch the suspicious behavior before the attack is even attempted. We mentioned already the port scans, and those are most often how attacks start, actually. All right, that's it on this topic. Hope you found it useful, and if there's anything left unclear, please ask your questions in the Q&A section or reach out directly to me in a private message. I'll be happy to help you.